Okay, I got that QR code. If you are tuning in right now, and I can see some of you are watching the 137th Global Star Party, The Age of the Universe, featuring, again, Dr. Uh, Bart J. Bach, and this is his second lecture with The Age of the Universe. So I think this is going to be a real treat if you like the last program. So, and who we got? Osmosis 007 saying howdy, internet people, and Mike Wiesner right now tuning in from uh, Arizona. So here we go. And it looks like everybody's here. So let's do this.
This is an image of something called M87. M stands for Messier. And Messier was an astronomer who was very interested in finding comets. But he didn't want to find duds, he didn't want to find false alarms. This is one of them. And you can see why, if you were looking at something like that in a small telescope, you might think it was a comet. And if we keep drilling down into why M87 is such a fascinating galaxy, it is an elliptical galaxy, and it's been known for quite a long time that there was this little thing of brightness that was spewing away from it. And now we know that that's actually a jet of material. When Hubble was launched, we had really good clues that galaxies probably had black holes at their centers. So M87 does indeed have a very massive, supermassive black hole at its core on the 2 to 3 billion times solar mass level, and that's a very massive, supermassive black hole. But it's also active. Why? So why are galaxies active? Not all galaxies are active. Just a few percent are active at any given time. Are they turning on and then turning off? That's an idea, you know, maybe there's some mechanical physics going on at the center of these galaxies where the black hole has an accretion disk and that material is getting spun up so quickly. We know there's very high magnetic fields that you launch a jet. And so this image is observational evidence that what we've been seeing for a while is actually being launched by a jet connected to that supermassive black hole at the center of M87. What we're seeing here is one jet, so we can assume that this material here that's making up the bulk of M87's huge stellar population is obscuring the other jet. In order to get a jet like that, you need a magnetic field to accelerate particles, and you also need a source of charged particles. So that means that you need, near the core of that galaxy, a disk of material, and that disk of material needs to be spewing in towards the black hole. It's got a huge amount of gravity. It's gonna suck stuff in. And when it gets close enough, it starts to accelerate those particles to ever increasing rates and then spews them out along magnetic field lines. We've got lots of particles and they are being accelerated at nearly the speed of light. The actual connection between having a supermassive black hole, an accretion disk, and launching a jet is still one of the mysteries of high energy astrophysics. How does that get launched? What is the actual physics between the black hole, the disk, and that jet?
Hello, everyone. This is Scott Roberts from Explore Scientific and the Explore Alliance, and welcome to the 137th Global Star Party. This show is being co-hosted by David Levy, and let me bring David on now. David, thank you for agreeing to do this, and it's more fun to host this with one of your best buddies in the whole world. So um, we have a really special show going on tonight with the second installment of a uh, film that we remastered from an original kinescope film of Dr. Bart Bach. And uh, last week we talked about the size of the universe, and now this week he's going to be talking about the aging of the universe. David, I'm going to let you take it on from here. If you didn't watch last week's program, uh, we didn't really get to communicate with you that David was a personal friend of Bart Bach, and he was his biographer. So he knows a lot about the man, and so I think that having David Levy here to talk about the scientist and the astronomer, and just the personal aspects of Bart Bach is really kind of brings the whole thing to life. The film that we have is from 1957, so you got 6 decades of legacy going on here. So I'll turn it over to you, David. Thank you for agreeing to do this. So,
Well, thank you, Scotty. And may I begin by saying that when I got this telephone call from you last Sunday with the offer to make me a co-host of the Global Star Party, I consider it one of the greatest honors I've ever received in my life. I was really overwrought, and I really, really appreciate you thinking of me, and I'm really, really honored and happy to be here.
It's honor for us and for me personally. So thank you.
Well, thanks, Scotty.
Thanks.
Today, I want to quote from my own biography that I wrote of Bart Bach. Here is the book. It's called Biography of Bart Bach, The Man Who Sold the Milky Way. And trying to figure out the title took almost as long as writing the book. But it was my friend Peter Chedecky who suggested the title. And for those of you who weren't here last week, I just wanted to say that I was driving him to the airport shortly after I relocated from Montreal, Canada, to Tucson, Arizona, Vail, Arizona, where I'm living now, actually. And I was taking Peter to the airport, and he said, David, your assignment, should you choose to accept it, is to interview Bart Bach for an article that I'm writing about him. And I said, Peter, I can't do that. Bart Bach is one of the most famous astronomers in the world. In fact, he wrote the introduction to one of my favorite beginning books, the Golden Book of Astronomy. And I still have that book, and it's a wonderful introduction. But that went on. I finally called him, and we were able to get together, and we started doing that. And as he was telling me about his life and his research, the problems that he had at Harvard, the joys that he had at Harvard and other places, and was really so exciting and so interesting to be with him. For my quotation today, I'm going to start by taking a few stanzas out of the Harvard Observatory Pinafore. Some of you may be familiar with that. Shortly after Harlow Shapley became director of the observatory, he got the idea that he would write the staff to put on a spoof of Gilbert and Sullivan's HMS Pinafore. And here are a couple of poems from it. In the cool night air with S&P, I wearied my eyes on photometry. Bright stars with H, faint stars with I, blue doubles reserved for a cloudy sky. So many close doubles were measured by me that now I am observing with photometer P. And I turned the dome with so grand a shock that I broke 2 windows in the Elliott clock. I burst the gas pipe, rolling the chair, and created a blaze for the winter's scare. For my worthy zeal, they requested me to try my strength with photometer P. This was really a joyful thing, and I think a lot of people a lot of the most famous astronomers of the generation that I was growing up in, who went to Harvard and were part of that, were just remembered it with such joy. The final quotation is going to be was was Bart Bach and his decision to leave Harvard. He and Priscilla, his wife's decision to leave Harvard. He said, before the Bachs left, Shapley treated them to one of his legendary parties. We left Harvard in great form, Bach noted. I always kept a bathroom the staff gave me at that party, beautiful one that lasted for over 30 years. Then, as Priscilla and Bart sat in Bach's seats, the students sang a farewell melody to the tune of Carolina in the Morning. And this is really not Carolina, but Karina, Etta Karina. Nothing can be finer than to guide an old Karina in the morning. Nothing can be greater than to follow good old Ada till the dawning. One of heaven's glories, that's what I go for. Twinkling little stories, I long to see much more. And nothing can be finer than to guide an old Karina in the morning. And I think on that,
I love that. That is wonderful, David. Thank you. Thank you. You don't often get to hear David Levy sing on this program, but
thank goodness.
occasionally you do. Occasionally you do. That's right. Okay, so this next lecture was done by WGBH. Janet Ivy Densing and I were kind of talking a little bit. I was getting to know her a little bit more, kind of backstage here. And she also has worked with WGBH a little bit. So, and I did too. I did a NOVA program for Mauna Kea for the 91 eclipse. So our crossroads, our pathways have crossed, and it's happening here on Global Star Party tonight. And I believe probably David Levy has been on WGBH as well for several programs, documentaries, et cetera. So, this next video, is there anything you want to add to this, David, about his Bart Bach's take on the age of the
Really,
universe?
I'm trying to think of when I was on WGBH, and I think it was probably almost certainly the time around our comet Shoemaker-Levy 9 colliding with Jupiter.
Sure.
And I remember being on a radio interview there and really enjoying myself there. And then on other things, when I went to Boston, visiting the headquarters of Sky and Telescope magazine, visiting Brian Marsden and Dan Green, and all these wonderful things. And Brian and I got to be very good friends. We argued about a lot of things, but we really got to be very good friends. And I really miss him. But as we're about to listen to Bart Bach give one of his famous lectures today about the age of the universe, I'm looking forward to reacquainting myself with Dr. Bach and also to the joy of listening to him give a lecture. So on that note, back to you, Scotty.
Okay, thank you very much. Well, here we go. Again, we're introducing Dr. Bart Bach from his 1957 lecture, The Age of the Universe.
Our topic is the age of the universe. Perhaps it would have been a little more modest to speak in terms of the cosmos, because what we shall be doing is to consider changes that are taking place in the universe and try to see how fast these changes, in other words, the universe as we see it now the solar system, the Milky Way system, the stars in the system, has that always been the same as it is now? The answer to that question is no. It must have been changing. Let's ask another question. If it has changed, can we roughly say how fast these changes are taking place? The answer to that question is yes. We can, in many cases, in a very definite time scale of development to our cosmical phenomena. So what we're going to do is to talk about the time scale of development. Let us start with a simple reference point. Because our times are going to be rather large ones, we must pick some fairly definite units and get these firmly fixed in our mind. The first one that I shall want to consider is that of the age of our own Earth. Our own Earth has an age of approximately 5 billion years. So, age of Earth equal to 5 billion, that is 9 zeros, of our regular years. That age has been determined by geologists, and the geologists have been helped by the physicists. They've done it by radioactive techniques, finding out how long it takes for rocks to change their composition, how many of the decay products there are around, and in that fashion it has been possible to find a pretty good figure for the Earth. 5 billion years is that figure. Now let's go out in the universe, start looking at our own Milky Way system, and begin with one of the photographs of a region of our Milky Way system in the constellation of Cygnus. Probably many of you know this part of the sky. It is not far from bright DNEP, the Northern Cross. And there on this photograph, we see the dots which mark the stars. We see the clouds of gas, here this famous North American nebula, shaped purely by accident in the shape of the continent of North America. That's a cloud of gas floating in between the stars. Therefore, we have our matter partly in space in these clouds of gas. Part of it is also in the stars. Roughly speaking, for every 3 grams of matter that we have in space, there are 2 grams squeezed into the stars, like our own sun and others, and there is 1 gram floating in between the stars in these clouds here. In addition to the interstellar gas, there is the cosmic dust. Look, for example, here at the Gulf of Mexico of our North American nebula. See how dark everything looks there. Why is that so? Because there is overlying this region a large cloud of opaque cosmic material, tiny little icicles that screen off the light from the stars that lie beyond. Cosmic dust, cosmic gas, and stars. That is what our universe is made of. Our own Milky Way system, of which this cloud is just one example, is a vast system in which the stars, the gas, and the dust are intermixed in about the same proportion that we had here. Here is a drawing of a large-scale map of our Milky Way. Every one of these clouds that you see here is really a composition of a great many stars, so many close together that they make the appearance of a star cloud. The stars are more numerous along the band at the Milky Way than at some distance away from it. In the Milky Way, they are not distributed in a perfectly regular fashion. In some parts, they are very much denser, like, for example, the Milky Way of our summer, of Sagittarius and Scorpio. In other parts, like the Milky Way of winter, of Taurus, and of Orion, there one finds much thinner part of the Milky Way. What is the place of our Sun in the Milky Way system? And what roughly are the dimensions of that Milky Way system? This drawing here shows this rather clearly. Let us turn first to the one on the right. In the one on the right, one has a view of our Milky Way system of stars, as viewed from a great distance above it, a couple of million light years or so. As one looks at the Milky Way, one sees that it is a flattened system in the shape of a wheel or of a watch, one might even say of a pancake because it is quite thin. And our Sun is just an average star, neither very bright nor very faint, in the outer part of the system. at the speed of light, which is 7 times around the Earth in 1 second. This is a scale of 100,000 light years. In other words, the diameter of the system is approximately 100,000 of these light years. The distance from the Sun to the center of our galaxy is roughly, because we use these terms Milky Way system and galaxy intermingled, the distance from the Sun to the center of our galaxy is approximately 27,000 of these light years. Seen edgewise, the system would have this appearance. It would appear like a flattened system with a central bulge very clearly marked. Again, with the Sun located in the outer part, 27,000 light years from the center. If we could go a long distance away from our Milky Way system and look back at it, it would probably appear something like this spiral galaxy or spiral nebula, as we sometimes call them. If this were our system, from here to there would measure just about 100,000 light years. Our Sun's position would be marked by this little black arrow here, and from here to there would be 27,000 light years. The Milky Way is highly flattened. It is really a thin, flattened system. It is probably in rotation around its center. And we ask how fast it goes. Well, from the Sun to the center, 27,000 light years, our Sun moves at a rate of approximately 140 miles per second in a direction something like this here. How long does it take the Sun to go once around the center? But that is a useful time to keep in mind. Can you see it? Here is the Sun, here is the center, 27,000 light years, 140 miles each second. The Sun and the Earth comes along with it. How long does it take to go once around the center? That interval, which we shall call the cosmic year, is equal to roughly 200 million of our regular years. Now, if you would keep this in mind as our second basic feature, that our Sun moves once around the center of the Milky Way system in 200 million years, we shall call this one cosmic year. So I return to the blackboard, and we write there that one cosmic year is 200 million regular years. 200 million, a 2 with 8 zeros, regular years. Now we can begin to write the age of the Earth in a slightly different fashion. It was equal to 5 billion cosmic years, and you see 5 billion regular years. That is 25 of the cosmic years. So, roughly speaking, since the beginning of our Earth, the Sun has moved approximately 25 times around the center of the galaxy. That is why we say that the age of the galaxy is 25 cosmic years. What sort of changes do take place in a period of the order of 25 cosmic years? Well, this diagram gives a rather nice sample of the sort of changes that take place inside a few cosmic years. Here we have a typical galaxy, an object with a mass and a diameter equal to that to an average Milky Way system. And we have lined up 10 different points, no 11 of them altogether, 11 different points from here to there. Let us assume that this one rotates around its axis, just like our Milky Way system. How will the shape of this line change? Well, as it rotates, the inner parts move faster than the outer ones, so this will be pulled out in a spiral-like feature. And look how beautifully it looks. One revolution later, one cosmic year later, in other words, a very fine spiral will have been produced in that interval of time. Many of the spirals that we see have this sort of appearance, and quite a few look a little more like the case after 2 revolutions, where we will find that things begin to wind up a little bit. The inner parts are winding, turning faster than the outers, and the spiral is really beginning to wind up. After 3 revolutions, we begin to see evidence that the spiral is getting too much wound up for comfort, that it becomes difficult to see the details of the spiral structure any longer. In other words, The spiral feature will probably last for something of the order of 2 or 3 cosmic years, not for 25 cosmic years. And changes must be taking place in our universe in intervals of the order of 3 cosmic years. Now, if we want to find out where these changes are most marked, then we come especially to the groups or the clusters of stars. Let us take the most familiar one of all, the famous Pleiades clusters, the famous group of the 7 sisters. Well, there are more than 7 sisters there, but there are about 400 stars at least in this grouping of stars. These stars will interact with each other as they pass by each other. They will be acted upon by the pull from the different field stars that pass it by. Those field stars may pull more on one star than on another, gradually have a tendency to loosen up the cluster a little bit. The shearing forces of the nucleus of the galaxy will be trying to tear the inner parts around a little faster than the outer parts, which as a result that there will be a tendency to tear the whole cluster to pieces. How long will the Pleiades cluster last? Well, we can calculate it. The Pleiades cluster should disappear from the celestial scene in just about 25 cosmic years. So now you see the Pleiades cluster. Wait 25 cosmic years, and gone it will be. It will not be there. We can therefore write on the blackboard, Pleiades cluster out in 25 cosmic years. So the Pleiades out in 25 cosmic years. I shall just write CY, C for cosmic, Y for year. The Pleiades cluster is one of the denser of the clusters of stars that we find in the sky. We ask what will happen to the more rarefied ones. I think all of you may know the second one, or a good many of you anyhow, the so-called Hyades cluster, a V-shaped group of stars tied into the famous bright star Aldebaran. The Hyades cluster has a rate of development that is faster than that of the Pleiades. You can see why. The stars there are pretty far apart, and these arrows here, which indicate the amounts and directions of their motion, are not all of equal size. In other words, in the Hyades cluster, some effects of the passing with field stars have already become noticeable, and we see the cluster slowly running away from each other, without probably enough pull to keep the brethren right at home and keep the cluster tied together. One can calculate what the future is of this cluster. In all probability, it will go to pieces in something like only 10 of these cosmic years. So here is a phenomenon that changes markedly in 10 cosmic years. So the Hyades out in 10 cosmic years. And as you see, things begin to speed up in our cosmic picture. Let us take one other very familiar cluster of stars, the famous group of stars in the Big Dipper. The stars in the Big Dipper, with the exception of the 2 end stars, this one and that one up there, all the others are moving strictly in parallel paths to each other, which means that they are now running together as a group. But because of the passage of field stars, the tearing effects of the rotation of the galaxy, this will not be a permanent arrangement. This will be a very short-lived affair because it has no gravitational pull of its own to hold it together. 2 to 3 cosmic years should suffice to disintegrate this cluster. So for the group connected with the Dipper group, we find that it will be out in about, say, 3 cosmic years. There are some of the mechanical evidences for development in our universe. Clearly, time intervals of the order of a few cosmic years begin to suffice to give major changes. Let's ask one other question. We have now the Pleiades. If they go out, if the Hyades disappear, are there other groups that will take their place? The answer to that question is probably no. Therefore, change takes place fairly rapidly in the universe. Now, when we look at some groups that are dynamically quite compact and safe, like the beautiful globular star clusters. These groups of stars, they are suns that are so numerous, so close together, that they really can all right for a long time purely mechanical. On a mechanical basis, this sort of a system is safe for 100 or even 1,000 cosmic years, and the chances of it going to pieces mechanically are slight. But then there come the other changes, the physical ones. And we ask now, what evidence can we get from the evolution of the stars themselves? What can we learn from them about changes taking place in our universe? Here in the diagram, you see our sun in the lower right-hand corner, compared in size to some familiar stars. We know pretty well how our sun behaves and why it behaves the way it does. Our sun is a star that gets its energy from subatomic processes. These processes work roughly in this fashion, that our sun is composed of many gases, among them quite a bit of hydrogen. The hydrogen atoms collide with each other, interact with other atoms, and produce helium atoms. And the one characteristic that one has about these helium atoms is that they will on the whole have a slightly smaller mass than the hydrogen atoms from which they are made. In other words, a little mass is lost while hydrogen is being transformed into helium. As a result of that, a star can burn up approximately a little less than 1% of its total mass and change it into energy. Our sun does that at a very slow and reasonable rate. It can keep on going for 100 cosmic years without any embarrassment. Some of the bigger stars do it a little bit faster. And especially when we come to the real big fellows, the supergiants, then the problem becomes really a serious one. And one begins to find some remarkable things taking place. Take, for example, a star like the one that is pictured there on the left. That is a star like Betelgeuse. A star with a mass somewhat bigger than our own sun, but not too much more, but with a diameter that is so big that Mars could turn in its orbit around the sun inside that particular star. To keep that whole surface burning at a temperature of 3,000 degrees requires an awful lot of atomic energy. The blue-white hot stars, smaller it's true, at the other end of the line, smaller it is true, but exceedingly luminous, have equal problems of where they get their energy. For here we have the problem. Suppose we have the sun right here at this point, one of these luminous giants right up here. If we take the sun as the one star, the luminous giant as the other one, the ratio of the masses of the two is about a factor 1 to 100. What is the ratio of their total luminosities? Well, for the sun, 1 again, the ratio of luminosity for this one is in many cases as high as 100,000 times as great as that of our sun. In other words, the masses 1 to 100, the luminosities 1 to 100,000. In other words, the atomic energy pump in the giants have to pump about 1,000 times as fast as those in the sun. In other words, if the sun can keep it up for 100 cosmic years, this poor star can only keep it up for 1/10 of a cosmic year, and it is on the way out in no time. What we are therefore looking for is especially the properties of the most luminous stars. They are stars that must be subject to very rapid and continuing changes. Now, when we look at these stars and look at their changes, we wonder where these stars occur per made. These stars occur especially in regions of the great gas clouds. In other words, it looks as though the gas clouds are slowly condensing in spots and beginning to change into stars. If I had to take a real example of the pre-stellar stage, I would go to this one here. I would take these little dust clouds, globules we call them very frequently in astronomy, little dust clouds that are present in some of these lantern slides and that actually are clouds of dust slowly being condensed by the pressure of radiation and by their own gravity. A cloud like that, present here at a given time, will collapse under its own gravity, will be pushed together by the pressure of radiation. What will happen? The particles will hit the other particles. Those particles will then be scattered. As they're scattered, you will find that you have the molecules forming. The molecules will go to atoms. And finally, as these things speed up and move faster and faster, the atoms will hit each other in their nuclei, and then bang, you have subatomic energy progressing outward, pushing against the star cloud, and a star will have been born. So the process is that of a gradual collapse followed by the formation of the atomic energy. These are the sort of things that have come closest to the pre-stellar state. How long does it take to form a star in that fashion? Something again of the order of 1 cosmic year. So all the evidence in our galaxy points to the fact that our universe has been going on for a time of the order of a few cosmic years. Let us now begin to turn to the universe of galaxies, the universe of Milky Way system. Here you will find in this photograph, these hazy spots are not stars out of focus, but they are Milky Way systems like our own, galaxies like our own, floating in space. We know that one of the properties of the universe of galaxies is that they all run away from each other, that they have velocities of expansion, that the universe generally is expanding. We know how fast one is expanding, that is at a certain distance away from us. We therefore know distance, the rate at which it is moving away. We know therefore too how long ago they were all close together. And now we might as well go back to the blackboard. For on the blackboard, we found that the age of the Earth was 25 of these cosmic years. That clusters developed mechanically in times of the order of 25, 10, 3, and so cosmic years. We found furthermore that new stars were being formed and were being formed all of the time. That these new stars were being built up out of clouds of gas and clouds of dust. These galaxies, these stars that are present now, they all developed in time ranges of this interval of time. Finally, we turn to the expanding universe, and we found that the galaxies themselves, running away from each other, indicated that they were all close together 25 cosmic years ago. Well, one thing begins to be quite clear, that beginning from the Earth, moving out into the Milky Way system, moving into the universe of galaxies, mechanically and from the physical evolution point of view, that 25 cosmic years is a pretty basic and important interval. And what I would suggest to you is that it is not likely that this is the age of the universe, but that it certainly is quite sure that 25 cosmic years is a very important interval in the development of our universe. What I've done today is to talk in terms of the simplest of classical phenomena. I could have changed this over and told you about other approaches to this problem. I have purposely stayed away from the creation of matter, from the new phenomena that have been suggested from time to time, but that are not yet accepted. In the most conservative fashion, one can say, we have now come to the point where we see evidence for change and development. 25 cosmic years is an important interval. Keep that in mind, and you are safe as far as cosmical development is concerned.
Well, that is awesome. That is awesome. So what did you think of that, David?
It was very emotional for me because I had never heard Bart giving lectures from he was at his prime. I met him when he was a lot older, and his accent was still there, but he was a lot less formal in the older days and those later days, and we got to be very friendly. But what you have offered in the last 2 weeks is introduced me to a different Bart Bach, a Bart Bach when he was younger. And even though this is like over half a century old, and that we now suspect that the universe may be as old as 13.7 billion years, to hear Bart talk about it back then, it's still relevant. He's right that the cosmic year, 25 cosmic years, is a significant portion in the life of the universe. That still exists right now. He is correct in a lot of other things, and I couldn't find anything where I thought he was definitely dated on. This was current, this was wonderful, and I just plain loved it. Thank you for enriching my day today.
Yeah, that's great. Yeah, I think everybody was kind of digging the fact that we were showing or introducing Bart Bach to a whole generation of amateur astronomers and people, stargazers out there that had never one heard of him before, but and if you had to see him at at the peak of his powers here. What did you think, David Eicher?
I thought it was marvelous. And, I think we should just pause for 1 second to understand that, for decades, Bart Bach, along with Priscilla, was the world's preeminent authority on the Milky Way galaxy, wrote the famous book, The Milky Way, but that was a popular book, essentially, that was based on numerous papers that he wrote, many in tandem with Priscilla. And I knew Bart just for the last couple of years of his life through David. And it was in Tucson and at the Texas Star Party and a couple of other places. And it was because of David's friendship with Bart and your biography project, David, that I got to know him just at the end of his life. And I thought what you said was exactly right, David. He was much more, there was a little bit less of heavy accent, then, and he was a lot more relaxed than the professor that we're seeing in these videos here. And I just thought we should also pause for a second and think about, this was 60 years ago, this film we're seeing, a little more than 60 years ago. That's the time differential in a very special era of astronomical research here that's equivalent to the time when Hubble discovered the nature of galaxies and the cosmic distance scale, up to the time of the first cosmological satellites being launched in the 1980s. This is a long time ago now, Bart's lecture here, and yet to a first approximation, the numbers here are pretty correct still, mostly, which is pretty amazing. He talked about the age of Earth being, 5 billion years. Now we know it's 4.543 billion years. It's a little younger than the sun, of course, at 4.6 billion years. The age of the universe now we know pretty well through the cosmological satellites, most recently Planck, of course, is 13.8 billion years, and that's pretty well known through a whole variety of means. But the cosmological effect is looking at fluctuations in the cosmological microwave background radiation, and applying that to the theory of general relativity in a somewhat complex way, and that gives us a pretty good estimate of 13.8 billion years. Other things that he mentioned were, to a first approximation, they're all pretty much true, which is pretty amazing after 60 years. He talked about rotations, the cosmic year, rotations of the solar system around the galactic center. He talked about 25 cosmic, we know it's 22 rotations that our solar system has made around the galactic center. And he talked about some open clusters too, and the ages of stars. And, we know that our sun, of course, stars are born in open clusters from nebulae. And it was cool that we caught Bart there talking about these little dark globules, that he used the term globule, David, which form protostars in those globules. And of course, they came to be known as Bach globules, very famously after Bart. But we know that the sister stars in our cluster are long gone after 22 rotations due to tidal forces around the galactic center. And so, the Pleiades, we now know its distance because of various methods, very accurately at 444 light years. It will probably dissipate in about another couple 100 million years. We know that the closest star cluster to us, as he mentioned, is almost all the stars in the Big Dipper asterism are in the so-called Ursa Major moving group. That's about 80 light years away from us. That will dissipate sooner. That's the relatively weak cluster in its latter stages. So maybe, it's about 80 light years away, and maybe about, 80 million or 100 million years from now will be dissipated. So these stars break up because of tidal forces as they orbit the galaxy. We know a little bit more about that now. But these are only refinements. We're only changing some of the numbers here by about 10 or 20%. which after 60 years and everything that has been discovered and known just in the last generation, which has been explosive, this is incredible. It's still, to a first approximation, a very accurate summary of the galaxy and what's going on in the galaxy. And, we didn't know the age of the universe precisely then. We do now pretty precisely, we think. But it's astonishing that so long ago, he had a pretty good first approximation on this whole field of numbers.
Right. Right. Well, gosh, David, I kind of pounced on David here saying, hey, David, could you kind of update us with latest numbers and stuff? And Mr. Eicher's doing this right off the top of his head. Okay, so this is, but it's no surprise. I mean,
it's the result of a wasted youth, Scott.
It's no surprise. He wrote a wonderful book about galaxies, which you can find on Amazon. So both of these guys, Mr. Levy and Mr. Eicher, have written a tremendous number of books. And certainly you should browse through Amazon and maybe Springer and astronomy publishing, Combat Publishing, for some of these books, because they're a real treasure. And if you meet them, they'll be happy to sign them for you. So, they do get out there. So, and you should too. I'm going to turn this over to Mr. Eicher right now. I do want to say that David is, if you don't already know, because I've said it many times, he is a great guy, very knowledgeable, very diverse in his knowledge base, from history to geology and astronomy. An extremely fascinating guy just to sit around and talk to. And you can do that if you go to the Starmus event, which is coming up here, which David will talk a little bit about, but and also just reading his column in Astronomy magazine. So they're still celebrating their 50th anniversary right now, and you can pick up that 50th anniversary special edition on astronomy.com. But David, you're fascinated not only with all these, various aspects of the universe, but you love the exotic. And you're going to be talking about an exotic object tonight, which is NGC 7008, called the Fetus Nebula. When I saw that, I go, right. Fetus Nebula. But it does look like a fetus.
It
so
does.
I'm going to let you talk about that.
Well, thank you so much, Scott. And if we ever, have doubted that amateur astronomers have too much time on their hands, all we need to do is look at the popular names of deep sky objects, right. And that proves it time and time again.
That's right.
And this one, we still have hundreds of objects here to work through. And so I will share my screen and share the right PowerPoint and start the PowerPoint, and we'll hope that we can. There we go. Thank you very much. And that jumped out of my way. And if you can see Centaurus A, we're in business, but that's not the right object tonight, as you said. So we'll skip it and go right on to NGC 7008. If ever you don't have enough to do in the summertime or the early fall evening sky, Cygnus, the constellation Cygnus, is loaded with spectacular planetary nebulae. And these foreshadow, of course, what will happen to, Bart talked about our sun and a little bit of stellar evolution there. About 6 or 7 billion years from now, long after we're gone on our planet, about 1 billion years from now, the oceans will boil off of Earth, which is going to kind of ruin the weekend. But long after that, when we're gone, our sun will evolve into a red giant and eventually a planetary nebula and a white dwarf remnant. And we will become one of these really amazing objects. But for now, we need to look at others that are out there. And NGC 7008 is another really good one. And there are lots of these in Cygnus that are really cool and somewhat large in terms of angular size and worth looking at. This one's in northern Cygnus. As Scott mentioned, it's sometimes called the Fetus Nebula. You can judge that, see that when I show an image here and see what you think of that. It was discovered by our friend William Herschel in 1787 from Slough. It's pretty faint, but it's fairly large as well. It's more than nearly an arc minute and a half in size and about 12 magnitude. It's V magnitude. So, if you get into a dark sky and have a 4, certainly a 6 or an 8-inch scope in a dark sky, you can see this object pretty well. It's about a light year in diameter, as most planetaries are before they really start to dissipate over their lifetimes of 20 or 30, maybe even 50,000 years in some cases, into the interstellar medium. So it's roughly the size of our solar system if we think of the solar system as being a physical diameter that goes out to the outer edge of the Oort cloud. So it's a nice challenge object. It holds up to magnification pretty well. It has a reasonably high surface brightness, even though it's kind of faint overall. And it has a 13th magnitude central star. So it's pretty observable in medium and larger amateur telescopes as well. There are 2 dark nebulae in the field that are fairly close to it, one from courtesy of E.E. Barnard and the other Beverly Linds. And you can see these in astro images. Certainly there are wide field pictures, if not visually. So here again, borrowing from Ron Stoyan's really nice Interstellarum atlas, you can see the nebula in the center there and the dark nebulae that surround it. And this is a pretty rich area, of course, of the Milky Way, northern Cygnus here, that's getting up relatively close to the border of Cepheus here as well. So it's a really nice area just to explore if you don't have anything better to do on those summer nights. This is it, and this is Adam Bloch's image that was taken from Tucson there, Mount Lemmon, and you can see what you think as far as is that the Foetus Nebula or isn't it? And you can see there are a couple of bright foreground stars that are right next to this nebula, and also, of course, you can see the central star there pretty well in this image. This is a Sloan Digital Sky Survey image that has been manipulated, as well enlarged and manipulated with some color and some contrast here to show a little bit more detail in the object here. And that's it. I mean, that's just a quick, this is an object that hasn't been super well studied, but this does lead us into a special issue. Not only do we have a list of, if Scott will put up with this for the next 10 years, of 400 more weird objects to talk about, but we took the best quarter of them and we made a special issue that's the January issue of Astronomy magazine. So if you get Astronomy, you'll get this issue coming up in a few weeks here that have the 101 weirdest of all objects, strange creatures in the universe. So that was a fun project to devote one special issue of the magazine to.
That is wonderful.
And as Scott said, we're going to have a 7th Starmus Festival. For unknown reasons, I got involved with these guys about 14 years ago, and Garrick Israelian, the director of Starmus, and Brian May, the co-creator of Starmus, who also happens to play a pretty good guitar in his spare time. And they have founded this science festival that's very popular, and we've had many, many Nobel Prize winners and astronaut explorers and musicians and other creative folks in all the sciences, astronomy, but also physics and biology and all sorts of things. And we've just had Jane Goodall has joined our board, and along with a number of very distinguished people and me, there's got to be one always, right? On our board. So we're going to have the 7th Starmus Festival in Bratislava, Slovakia, this coming May, in the middle of May, and it'll be quite incredible. It's about 5 weeks after the eclipse in the United States here. You can successfully enjoy the eclipse and then go relax at Starmus and hear amazing talks that we're going to have, and we'll also have a lot of entertainment over there. It's easy to get to because it's very close to Vienna, Austria, which is easy to fly to, and we will have some rock and roll and some fun there, as well as a lot of science. So we hope you'll join us at Starmus. And Scott, that's all I have for tonight. I will stop sharing my screen.
No, it's great,
And Scott, you'll be there. We'll have a star party, which we did last time in Armenia. We'll do that again, and we will have distinguished speakers that include David Levy, among others.
Well, I'll tell you, I've got this big QR code next to me here, and we're going to talk about that in a second. But being at Starmus is just an amazing experience. That's all I can tell you, because you are surrounded with so much, brain power. I mean, they could light up, London, Vienna, and several cities. But it's in a very relaxed atmosphere. You have the opportunity to see these people in action, live in front of you, and you're mingling with them at many of the events that go on, and it's going to go on for what? A week?
Most of a week, and we'll have some additional things going. There's going to be an astrophotography school. Scott, I think you'll be involved with that as well. The main festival itself, which are mainly talks and shows that involve entertainment as well, goes on for nearly a week, and you do get to get up close. We've had all the Apollo astronauts and many Nobel Prize winners, including people who will, Emmanuel Charpentier is one example, who may extend your lives, through CRISPR gene splicing technology. But many prominent scientists, as well as astronaut explorers and rock stars too, are into it. And we have Rick Wakeman and Peter Gabriel involved in our board, and many others as well.
Jean-Michel Jarre, he's going to be there, right?
Jean-Michel Jarre, who's put on the largest concert in human history in Moscow. There were 3.5 million people outdoors at his concert. It's in the Guinness Book of World Records. He will be there as well, and he's a super nice guy. And and Brian Eno has been involved, and lots of other of the more intellectual rock and roll folk, if you will. So it's going to be a great time again. We had about 5,000 people in Armenia. It'll probably be about that size again. But again, Scott, as you said, it's an opportunity to mingle with these people, to talk to them, to get close, to maybe have a glass of wine.
And never before in history could you do this. I mean,
it's quite.
I'm sure Einstein would have loved to have been at something like Starmus.
Starmus for stars and music.
And music.
The derivation there. Yeah. So join us if you can. It's actually very affordable to go to the event. Most of the cost for most people is is transportation, and you can fly to Vienna pretty easily, actually, so it's a lot less intimidating, even coming from the United States, than you might think.
Awesome. Yeah, get your passport ready. So Thank you so much, David. That's great.
Thanks, Scott.
That's great. Okay, so our next speaker is Janet Ivy Densing. Okay, she is a winner of the Sally K. Ride Award from the let me get this right, the American Astronautical Society, and she's a fellow Solar System Ambassador. That's a program I joined up with, but I don't really hold a candle next to Janet Ivy Densing with all the amazing stuff that she's done. She's had a life in entertainment. She is an incredible lecturer. She's given TED Talks before. She's someone that actually should be at Starmus. So, and this QR code next to me is a QR code that you can scan. Look, if you guys have not bought your eclipse glasses yet for the April 2024 eclipse, you can get them directly from through this QR code, and this helps support the amazing stuff that Janet does with her outreach and education. She was, I think you did a program today for, which country was this?
It was girls in Pakistan. and just a darling 10, 11, 12-year-old girls who love space and the stars. But the great news about my partnership and this affiliate link, you can order any of the glasses on the website. There's still some Cyber Monday deals going on, but most importantly, 10% of all sales, if you use this affiliate link, this QR code, goes to St. Jude's Hospital in Memphis. Paper Optics located in Memphis. I grew up there, and I'm super excited about April 8th. But I have to tell you, David Eicher, it's like to see that this Fetus Nebula that William Herschel played a part in some of its discovery. You know, we all know that he discovered Uranus and would have loved to have named it George's star. But what I also love to tell students is that he was a great brother. His sister, Caroline Herschel, was going to be doomed to be basically their mother's kind of like maid until he said, no, no. So William Herschel, among his many contributions to astronomy, also was a great brother, taught his sister how to sing opera, play the piano. And apparently Caroline hated it at first, hated those cold nights. And then we all know that she also made some fantastic contributions to space and astronomy, all because of a good big brother. So I love telling that story because the man is more than just discovering and naming and discovering Uranus there. But what I want to talk to everybody tonight, you guys are all talking about the age of the universe. So when Scott called and says, how do you explain that to students? Sometimes it's best to give them something that is life applicable. So I'll use a bit of math. I'll trick them into like solving something cosmic, because I believe along, if you've never heard Brian Greene say this, it's like I'm borrowing it from his book, that we must make science the most attractive, the most passionate adventure story that we could ever tell. And that's how we get students in a world where we kind of like stay on our phones like we're reading some great ancient scrolls or scribe. It's like it's time for us to realize that creativity is beginning to lag. And so what I love to do is to like tell it like it's like some like great Star Wars story, only it's real. And then to get the kids to like sneak in the math and the science, and then they fall in love with it. What I like to do is divide 13.8 by 24. And so that instead of calculating it in the billions of years, let's sneak it on down to a 24-hour day. You divide 13.8 by 24, and you're going to get 575 million. And so then you begin to go that every hour on the clock is about 575 million years. And then it's like you can sort of scale through time using that. And that's just one quick way, especially with elementary and middle school students, which is usually kind of like my general audience. So, but grander than the age of the universe. And it's like, I love it when kids actually are like, I'm going, how about these new things that have been discovered by the James Webb Telescope? Are they galaxies? Are they black holes? Or should they be as composed as they are? We don't expect the universe to organize itself like that. And so it's very fun to hear their feedback. We were speaking a little bit before we started the broadcast that sometimes you can be around 10-year-olds that will stump you with all of their knowledge, and you'll go, oh, yes, please continue, Professor. I always like to put them in the point of power when they know a lot of their facts. But I'm going to share my screen here, and we'll start here. Let me go into slideshow mode here. There it goes. So there's a couple of ways to follow me there on Facebook and LinkedIn. My Instagram is weird because it got hacked back in September, but I promise that's me now. And you can always find great kind of activities and hands-on experiments on my website at janetsplanet.com. But one of the things that it's like, again, the time thing for kids, it's still elusive, right? It still moves entirely too slowly. So what I continually love to do is to try to give them some way of scaling the solar system. Pardon me. And again, I know this is very lo-fi, but a lot of times when I am working with students to get them out of the screen, out of the kind of video game mode, it's like we're going to go super lo-fi, and you can literally, following this model, that you can take squares of toilet paper, we'll start at the sun, and then by the time they roll it out, it'll take up about 42 feet of space. And it's the most fun. And if you do this outside, you might have to have a few rocks or pebbles along the way, and they can mark them as they go. And it's a matter of being also, kind of scientific, and we'll go, oh, wait a minute, we have to measure this correctly. But this is just one quick way, and you can find this at greatbasinobservatory.org. And so I like to do this one, especially with smaller kids. But if you've got older kids, my next favorite one is 1,030 yards. So it's great to kind of like, it's best if you've got like an outdoor place. You don't necessarily have to do it in a straight line. You'll cover about a little over half a mile doing this, but you can come back. If you don't have a straight line, you can go in a circle, and all of a sudden it becomes really aware. So we'll kind of like set where the sun is, and then we walk 10 yards. And the other great thing is, again, sorry for any international folks that are watching, we're still lagging way behind in schools, where in the US we're not teaching as much metric. So that's the fun thing, to convert all of the yards into metric things. So that's another great math way that we can do. But what's fantastic to see students really go through is we'll start by going 10 yards. Then we, go another 9 yards to Venus, and then another 7 yards to Earth. And then all of a sudden, by the time that we're going from Mars to Jupiter, now we've got to go 95 yards. And they really begin to see what that is. And they're like, whoa. And then what we'll also do is we will begin to mark these places with something as small as, say, a peppercorn, and we'll tape it to, I don't know if you can even see that there. We'll tape it to an index card. And then it's like, when it's all said and done, we'll use different things. You can use kind of a pinhead for Venus and Earth. That's about probably 800ths of an inch. A peppercorn might be more like 300ths of an inch. And then you can use like a pecan or a walnut for Jupiter and Saturn. Again, you have to remind them the planets aren't exactly to scale at these distances. We wouldn't be able to see them at all. But when you get kids that, again, are inside a lot, and then we're walking over half a mile to go from one end, from the sun out to the Kuiper belt, it's so fantastic. And again, it's just a way to get it in their bones. For me, as probably a kid, that it's like I needed to understand it. I needed to feel it, dance it, sing it, and kind of like kind of embody what all of these things mean. That for me is the best way I know how to really drive this home. The last and most fun way is I love to be able to give kids a way to have their pocket solar system. And it's like, you can almost say a bit of this is a golden ratio. You just take about 1 meter of paper. This might be longer than that, but all you have to do is your first fold is just to half it. And then that center of this becomes Uranus. So you mark that as Uranus. You take that in. You'll probably, what I usually get kids to do is draw a yellow line here at the top for the sun, kind of draw a little kind of like peppered little place with all of the things out there in the Kuiper belt and at the bottom. And so then you'll take from the Kuiper belt to the middle there with Uranus. This next fold will become Neptune. And so you've got that. Now, here's where I think it becomes so super fun. And this is where kids go, no, there's got to be more space. It's when you start folding here. That next fold becomes Jupiter. The next fold becomes Saturn. And all of a sudden you're down to this much space, and you're like, wait a minute, we don't even have the inner planets yet. Then that next fold becomes, Saturn, Jupiter, Mars. Okay. So did I do? Yeah, I did that funny. I'm looking at it upside down. Sorry about that. So we get to Jupiter, we do another fold, then we've got the asteroid belt. And now it's like all of a sudden we've got even less paper, and we do one more fold there. And now we're at Mars. And then you can kind of do three little folds here. And then you can have the inner planets. And all of the kids will go, wait a minute, there's all the inner planets here and all this space and in between, and the vastness of our solar system. And this is a fantastic thing. What I've done is give Scott many of these links, and hopefully he's posting some of these places that you
Yes.
can find this in the chat there. But again, it's fun. The kids can decorate their pocket solar system. There's some great stickers of the solar system you can find on Amazon if you happen to be a teacher, or if you're an astronomer out for a star party. It's just a way to kind of get a miniature model of our kind of like solar system and our place in it. And then here is, let's see, I'm going to pause this really quickly. One of the very favorite videos that I love to play, there was a group of guys who decided to go out into the desert and take 7 miles of desert and scale the solar system. Here it is. It's so beautifully done, and I'd love to share this with all of you.
If you look up an image of the Earth and Moon, you're going to get a picture where they're quite close together, something like that. But in reality, the Earth and Moon are about that far apart. That is the Earth and the Moon to scale. Taking the same concept, but for the solar system, every single picture of the solar system that we ever encounter is not to scale. If you put the orbits to scale on a piece of paper, the planets become microscopic and you won't be able to see them. There is literally not an image that adequately shows you what it actually looks like from out there. The only way to see a scale model of the solar system is to build one. Welcome to Black Rock Desert. This is Alex. I'm Wiley. He's going to be behind the camera. I'm going to be probably making a lot of mistakes on camera. We have 36 hours to measure the distances, trace out the orbits, and set up a time-lapse shot from up on top of a nearby mountain. To create a scale model with an Earth only as big as this marble, you need 7 miles of empty space. So that's why we're here. Why did you guys come? I don't have a job. At this scale, the sun is 1.5 meters, so about that big around. So we are driving right now to Mercury. We've arrived. Venus is the same size as Earth. There's a world in my pocket somewhere. And Earth. And this is Mars. Got a couple of robots rolling around on that one. Once the time lapse is ready, we'll drive each orbit with a light. Hopefully you'll be able to tell just how big they really are. Onward to the outer planets. Jupiter. Saturn. That tiny light out there is our sun, just over a mile away. Sun's way, way out there now. So this is it. This is the edge of the solar system. So right now it's about 7 a.m. We just woke up right before the sun's about to rise. We are on Earth's orbit. Wiley is over there holding our sun. Cue the dramatic sunrise music. So if we've made our model correctly, your perspective from where Earth is on the model will match your perspective from standing on real Earth. So if you look back at the sun, you will see that the model sun and the real sun are the exact same size. That's how you can tell that the proportions are correct. There are 24 people in the entire history of the human species, billions of people, who have actually seen the full circle of the Earth with their own eyes.
Following the breakfast, the astronauts went to the soup room where they donned their spacesuit.
This is man's attempt to get to the moon.
0. We have liftoff. Liftoff at 7:51.
In Earth orbit, the horizon is just slightly curved. When you head on out to the moon, that horizon slowly curves around and upon itself, and all of a sudden you're looking at something that's very strange, but it is very, very familiar.
Oh my God, look at that picture over there. Wow, is that pretty?
You can put your thumb up, and you can hide the Earth behind your thumb. Everything that you've ever known, all behind your thumb. Nothing bigger than that, way up there. It's really beautiful. You can cry.
That's what I really wanted to try and capture. We are on a marble floating in the middle of nothing. When you sort of come face to face with that, it's staggering.
I just love that video, and thank you so much for indulging me and allowing me to share that with you. What's really beautiful to watch when I use this in my live performances, when I tour my solar system show around the country, is that when they say you can put your thumb up, and Jim Lovell's talking, you put your thumb up and you can hide the whole world behind your thumb, the kids in the audience will hold their thumb up. It is so precious because all of a sudden they're getting this concept. The last little thing that I will quickly just share with you, again, it's combining math. We're going to make math seem like magic and very like awesome, but you can literally take just a ball of clay. It's usually, they call for 3 pounds of clay or Play-Doh. You can always make it. And then we divide it into 10 equal parts. And then this is where it gets crazy, folks. 6/10 to make Jupiter, 3/10 go to Saturn, and only 1/10 of this ball goes to everything else. And then you go, you divide it up into tenths again. 5 more tenths goes to Saturn. Saturn's gobbling it up over there. What's happening? 2/10 to make Neptune, 2/10 to make Uranus. You really have only kind of like the remaining clay, kind of 1/10 for all of the rest of the stuff. And then you'll fourth it and divide it even more. And then by the time that you are really finished, it's really kind of like, let me see, I think I put that slide in there somewhere. All the way down here, let me show you where it is. It's a lot of steps to this thing. And let me put it up here real quickly. It's just that you'll see that by the time that you divvy it out, and again, the kids are all going, how is that possible? How is that we only have this much for all the rest of everything? And it's a great kind of visual way. You can see, and I've done it many times where Pluto really is just barely perceptible. But I hope you guys have shared, if you've enjoyed any of this, please reach out to me at janet@janetsplanet.com. It is one of my most fun things is to share how we can take like super lo-fi ways and help kids understand and begin to grasp the largeness of what we are. And I think that it's just incredible that we get to be on spaceship Earth, that we are all thermodynamic miracles, that the chances of us being who we are as we are with our unduplicable biological signature is 1 in 400 quadrillion, that the chance is greater, the probability is greater that we not be here, like 10 to the power of never, and yet here we are. And that we are part star stuff and iron in our blood, calcium in our teeth, carbon in our DNA, related to the very same elements that exist in the hearts of stars. So if I could share anything with you guys tonight, whether you're talking to children about the age of the universe, the size and scale of our Milky Way, and kind of like the things that are hard to kind of conceive, is really allowing them to kind of like fall in love with the wonder, create that best adventure story that you possibly can, take them on the best kind of like journey of their life. And I think that's how we get our next generation of astronomers and explorers and engineers. Thank you so much for letting me speak tonight.
Wow, that's awesome. Aren't you guys glad that I brought or invited Janet to be on tonight? I am just beside myself. Your presentation is fantastic. I know that people that watch this program, a lot of us think about ways that we can get youth into science and astronomy. And certainly astronomy is a big and easy gateway for people to get more scientifically literate. But it takes people like Janet Ivy Densing to really, bring that energy, that passion, and the knowledge and skill to make it all happen. So, I'm going to bring on. We want to thank you again. This QR code here is going to
Get your
help.
glasses. It's like it's going to be a phenomenal event on April 8th. But thank you guys so much for having me. I'm going to stick around in the background and listen to the other great speakers. What a thrill and privilege to be on with you amazing people tonight.
Thank you so much. That's great. So I will also bring on John Goss. Now, John is with the Astronomical League. John, what did you think about Janet's presentation?
That was it's always pretty incredible to talk about the size of things, both distances and masses and just physical sizes, especially in our solar system. I myself can go over this time and time again, but I'm always thinking, wow, space is pretty big. Yeah. And what we see on television and science fiction shows, you think, yeah, you just go from here to there and that's your story. Not that easy. It's all, even the closest is pretty far. The moon itself, pretty far to get to. It's far. So yeah, I thought that was pretty cool.
Wonderful, wonderful. Okay, so we are at the part of the Global Star Party where we talk a little bit about the Astronomical League. Wow. The Astronomical League is the world's largest federation of astronomy clubs with over 300 member clubs, but they also have members from around the world with their membership at large programs. So to become a member, you either join a club that's already a league club, and there's many of them across the United States, or you can go to www.astroleague.org and join up as a member at large. But they have incredible observing programs. They have an extensive series of awards that are given to youth with the National Young Astronomers Award, all the way up to programs like the Leslie Peltier Award that recognize lifetime achievements. Jack Horkheimer is also still with us with the Horkheimer Award, also for youth. And So many more. I think you guys have, as far as observing programs, you have something like 80 observing programs. No other organization has this. So, and in my mind, no other organization does as much as you guys do to support amateur astronomy and help people get more into this lifestyle, because it's beyond a hobby. So,
It is.
and
It
I
is.
know it's beyond a hobby for you,
Yeah.
John.
Well,
So,
it's a big universe out there, so
yes,
you got to have all these programs to try to capture at least part of it and make it
right.
worthwhile for people. But yeah,
Okay.
thank you, Scott. When I first saw what this general theme was today on Age of the Universe, I thought, how am I going to tie all this stuff in? How am I going to tie that in to what I'm going to say? Well, this is how. Um, it's become a family joke that when my grandkids ask me how old I am, I tell them, well, I'm old as dirt. And they go, come on, Gramps. Yeah, I'm Gramps. Come on, Gramps. How old are you? How old are you really? Well, I'm old as dirt. Well, how old is dirt? Well, dirt is as old as the mountains. Now, I live in Virginia, pretty close to the Appalachian Mountains, and they are upwards of 480 million years old. So dirt has a it's pretty old. So they say, well, how old are the mountains? I go, well, they're a lot younger than Earth. Well, how old is the Earth? Well, it's a lot younger than the universe. Well, how old's the universe? A lot older than dirt. And so on. We kind of get in this circular reasoning. So I think if you're a grandparent, you may have come across this type of talk with your grandkids now and then. But it does show something about how old the universe really is. It is a lot older than dirt. Before I go to my slides, I want to show you something right here. You might, if you're old enough, you might remember this album back in 1970 by Cat Stevens. He has a song, which I'm not going to play, but we're going to kind of refer to. He has a song called On the Road to Find Out. And it's about a young man who leaves home because he wants to see the world, see the universe, clear his mind of all this stuff and trying to understand. Well, that's kind of what amateur astronomy is all about, in which we want to leave our earthly world behind and go out and look at the stars and see what's going on. So with that in mind, let's like to share my screen, maybe. See if I can do this. Excellent. So obviously talk is called On the Road to Find Out, Triangula. Now, what is Triangula? There's a constellation out there called Triangulum, and that's what we're going to go to. But I did choose this particular title for a particular reason. On the Road to Find Out. Well, Cat Stevens, who wrote the song, he goes by Yusuf now. Basically, he said, well, I left my happy home to see what I could find out. I left my folk and friends with the aim to clear my mind out, and so on. So he wants to look up, he wants to see what's going on. He wants to clear his mind out and understand what is going on with the world. And that's what we're going to be doing here in just the next few minutes as an illustration. Why do we spend time under the stars? Top 10 reasons for stargazing. Reason number 2. I'm not going to go into all the 10 reasons. I'm just going to stick on number 2 here. Seeking meaning and place in our lives and achieving inner peace and contentment. I think a lot of us go out under the stars, and before we actually start looking through the telescope and fiddling with all this stuff, we like gazing at what's above and trying to understand and see what the stars really are above us on that particular occasion. So one thing we like doing is looking up, seeing the stars, and seeing that they're there every night. The same stars are there on that particular date every year for many years past and many years in the future. Just as an illustration, right here on the right is a star map that I happen to have a book from 1887. gives a star map of the fall sky. Of course, it's not a great map, especially with today's maps, but you'll get the idea. It shows you some interesting stuff on it. A lot of recognizable constellations that we see in tonight's night sky, such as Aries and Pisces and Pegasus and Perseus and so on. But right in the center, there's a constellation called Triangula. Well, there is no constellation called Triangula. There's Triangulum, and there's a reason for that. Go on here. You know, in each season, I think what I like to do is each season when I go out, I try to find a particular constellation in the sky, one that not everyone's going to be looking at. I'm not going to, of course, you go out tonight, you might go out and see Perseus or Cassiopeia is probably the one people would want to look at. But there are other ones out there. In the springtime or in the wintertime, people like looking at Orion. Well, I always try to find the one right below it, Lepus. Kind of a goofy looking rabbit. In the spring, I like looking at Corvus the crow. And in the summer, Delphinus, and it's a nice one in the summer. These are stuff that we all know, but we really don't look at. And you go out in star parties and people are showing stuff in the sky. They don't jump on these constellations. But I like looking at that because these are the ones that come in year after year. And the fall, we have Triangulum. Now, there are different ways of looking at this constellation, but I like portraying it as a tubular bell, not as an architect's triangle. But anyway, you have this constellation, basically 3 stars, but not really 3 stars, because Gamma is really a combination of 3 stars, fairly close together. So you get to know Triangulum, you get to know Delphinus and Corvus and all that, and you realize that every November 28th, you go out and look, Triangulum's going to be right up there in the sky. It's just kind of an old friend, and people like looking at that. Triangulum, okay, it's called that today. Roughly 100 years ago, up to 100 years ago, it was called Triangula because it was made of there are actually 2 separate triangles there. The Greeks saw it as a constellation called Deltaton because it looks like the Greek letter delta, kind of an elongated triangle. But then in, I don't know, 300 years ago, Johannes Hevelius made 2 triangles in there called Triangula, which is why it is. But in 1928, with the IAU chopped down the number of these constellations, they got rid of Triangula and just made it 1 triangle. This is a kind of a pretty lame shot that I took the other night, and I'll identify some of these now, but it has Triangulum right in the center. So every November 28th, or whenever I took this a week or 2 ago, you go out and look, Aries will be in the same spot. The Pleiades, Perseus, Triangulum, Andromeda. These are friends in the sky. They're always there. This is a big reason for going out and looking at the stars, because before you get looking at all the deep sky objects and all this other stuff in there, you can see these and you know, yeah, good. Everything's pretty cool. Everything's like it should be. But then pretty quickly, you want to learn more, you want to see more. So you want to look deeper into the sky and see what various areas have to offer, including Triangulum. Well, let's do that. We have a map here of the fall sky. Okay. You know, you got Orion's rising over there in the lower right or lower left, sorry. Pegasus is in the upper right, and you got all the stars in between. So let's zero in on Triangulum. Well, the way I have it drawn here is that there are two actual triangles, Triangulum majus and minus, which means larger and smaller. The Triangulum minus has been wiped off. It's no longer there. Stars are still there, but the little lines connecting them are no longer represented. But as you can see that there are a number of deep sky objects in this constellation, which you can occupy yourself with and looking at and trying to enjoy and understand, which we're going to tackle some of these in just a moment. First thing, though, if I get remember my slides. Okay, here we go. Age of the universe as applied to Triangula. We have the Big Bang, about 13.8 billion years, along with our bumper sticker that the astronomically offers of 13.8 billion years. So you can shove on there instead of having your half marathon, you can have the age of the universe right there. You got first galaxies appear about 12 billion years ago, 8 billion years ago. You have the formation of Delta Trianguli. That's one of the stars. So it shows how old some of this stuff really is. Formation of the sun, which we were just going over a few minutes ago, 5 billion years ago approximately. Coalescence of the Earth, 4.6, 4.5 billion years ago. Light from 3C48. Now, the reason why I include that is simply because C348 was the second quasar recognized as such, and that is in Triangulum. Life begins on Earth and so on. But then we go down the list and we see, where do we got that? The beginnings of Appalachian dirt. So that's how old I am, right there on this chart. Present day Earth, about 450, 480 million years ago, was the beginnings of Appalachian dirt. In the future, well, we'll just have to see. We think merging of the Milky Way and Andromeda galaxies will be in another 5 billion years. So this kind of gives you an idea of how long things are in the universe, how long ago it happened and what's going on. Let's take another look at Triangulum in the sky. This is a really nice picture. Thank you, Terry Mann, for doing this for me. Captures it pretty much what we want to look at tonight. You can see up at the top of the page or the screen, you have M33, probably the most well-known object in Triangulum. A lot of people like looking at, but it has a number of other items as well. And we're going to go through some of them right now. Iota Trianguli. It is a double star, pretty tight. You have to use high power to see it, but it really is there. You put in your high power eyepiece and you'll see that it actually is 2 points of light in my drawing, one kind of golden, one kind of bluish. We have another double star, 15 Trianguli, nice looking thing. This is something that you can see in binoculars. Again, one yellow or orange, gold, and the other is blue. This is something to take a good look at with your binoculars when you're under the sky, when you're under Triangulum and all the other stars. This is something I just don't know about. I have to know myself. It's called David's D. It's an asterism. And you can see it kind of looks like a D. Okay. Now that's something kind of neat to look at. You don't need a high power telescope to see this, but it's completely different. It's an asterism, meaning that these stars aren't physically or gravitationally bound to each other. That's something to look at. But now let's look at M33. This is the one that people like to look at in Triangulum. This is a drawing that I made, and you can see M33. And there's also NGC 604, which is actually part of M33. It's a humongous star-forming nebula in that galaxy, and you'll see that right next here. A friend of mine, Ed Dixon of the Roanoke Valley Astronomical Society, took this photograph of M33, and you can see the galaxy, of course, and NGC 604 with it.
Very nice.
Now, I thought it would be interesting to compare the two, direct comparison of what you can see through a telescope with what you're going to end up with a really nice looking astrophoto. Let's do that. So these are the two shots side by side. M33, you can see the bright core of it in both the galaxy image and my drawing. And 604, kind of a hazy smudge in my drawing, but you can see it in the photograph. So they match up pretty well. These things are in the sky, and they're all interesting to look at. It's something for you to take your time to do. I'm trying to get through this as fast as I can here, so I won't take up too much of this time. But when you do this, when you go out and go under the stars, maybe unaided eye for a little bit, maybe with binoculars, with a telescope, you start thinking, gosh, this is all pretty cool. What does this really mean? What have I done tonight? Well, you have made some constellation friends now, which are going to be greeting you every single November, forever. And you also have seen things like asterisms and double stars and galaxies, all in your journey on the road to find out what's really up there, find out what it's really all about. So there you are on the road to find out to Triangula, to the two triangles. I'll leave you with this. And if you have any questions, I'll be happy to answer. But I'm encouraging you to go out when you can, get a look at the sky, make some friends with the stars, and you'll see these things year after year, always. So thank you, Scott.
Thank you. Thank you so much. Wonderful.
Thank you.
Wonderful. Our next, oh, before I go, I did want to just mention that the Astronomical League does have an annual Astronomical League convention. Can you tell us a little bit more about that, John?
Yeah, in 2024, it'll be July 17th to the 20th, held it'll be focused in Kansas City, actually Overland Park, Kansas, which is a suburb of Kansas City. And it will be both virtual and in person. So hopefully we'll have the best of both worlds in there. So the talks are being worked out and how to do this. That's all being worked out right now of how to handle the virtual versus in-person part. I hope people like yourself will be there. I myself will try to be there this year. We'll see how it works out. July is an awfully busy month, awfully busy. But I'm looking forward to it. And I'm looking forward to seeing a lot of new people there, and as well as some of the people I've met in the past. It'd be good to seeing them again as well. But it's always nice meeting new people. It's a great program to introduce people to astronomy and the night sky.
Well, people make friends at this event a lot, and you can make friends from literally people that are from around the world, and see some great talks. Go to their barbecue, go to their after hours events, that they have, and including they always have a star party. So it's pretty amazing stuff, and so you definitely want to be hooked up with the Astronomical League, and you want to go to the Alcon event. So if you can at all make it.
You betcha.
And I'm sure John Goss will be there, and I plan to be there as well. So, okay, thanks so much.
Thank you.
All right, we've been up here in the United States. It's time to go down to the Southern Hemisphere, to Caesar Barolo. And we used to call him 100-mile-an-hour Caesar, and that's because he would be out on his balcony in Buenos Aires, sometimes with some very high winds, but still making images with his telescope setup. Caesar likes to encourage people to observe from the city, to observe from their balconies, from their backyards, and then when they can, to go to some really cool star parties and go where it's dark. Caesar lives in Argentina, where he has the best of both worlds, and he works at a telescope shop, which I can let him tell you all about.
Yeah, thank you, Scott, by invite me again. It's a pleasure share the sky from Buenos Aires with people in anywhere. And it's a pleasure. Tonight, we are lucky because we was expecting to have a storm coming earlier, but the storm is coming from the southwest, but slowly. And at this moment, we don't have big clouds. Really, it's a clear sky. Well, let me show you a live picture of Tarantula Nebula that I took in now. This is a live stack. Can you watch my screen?
Yes.
Here. Okay, here is the nebula, and now we have 12 minutes of exposure. Actually, I didn't have a gray polar alignment, and this is why when I use the live stack system in SharkCap, this is the part of the picture that I am losing. Here you can see, but I am expecting that because
all the stars are lined up. Yeah.
Yes. this nebula is in the region of the Big Magellanic Cloud. Is a really a great nebula, really, really big, really bright, and it's in another galaxy because the Big Magellanic Cloud is an accessory galaxy. It's a nebula that we can watch from here to another galaxy with details, and are at 160,000 light years. It's really different, the distance, because maybe you know that Orion Nebula, it's only 1,600 light years, or you know, it's a distance different. Maybe tonight that we were talking about the age distance of the universe, is very interesting to consider this. Well, I'll stop in 14 minutes, I'll stop the exposition. I'm using a very, very small, very small, you know, very small number in the gain of the camera, the sensibility of the camera. I'm using a small amount of number of sensibility. And another thing that I using very changing. I'll stop the stack. I'm stopped to stacking, sorry, the image here, save here, and now we are watching. I'll stop. Okay, now it's a live image. Okay, the another image that I showed you was stacked image. Okay, I put the gain to watch in a single pictures, and I'll center now. The change that the people can see is, of course, that I'm changing the gain of the camera, the sensibility, the electronic sensibility, and the time of the exposition time. And okay, I'll move. This is the best way to show because I'm moving the telescope, Scott. And you can see that this is new. This is live. You can see the difference between.
Yes, you can see the star trails there. This is a live
star
image
trail,
for sure.
yes.
For
And
sure.
something that is great because you have an area of the large Magellanic Cloud. Next week, if we are still lucky to have clear skies, I'll put my camera with an open field of vision, more open field of vision, to show maybe the shape of the galaxy of the. I'll using a strong narrow band filter maybe to show a more field of view image. Of course, that it will be great to show to the people where is the nebula inside a galaxy very near to our galaxy, or to Milky Way. This is a really precious treasure of the sky in our hemisphere, because it's really very interesting. Maybe let me try if I can show you with more contrast. a live image. You can see the nebulosity. Sorry that it's not easy, but maybe if I change here, maybe you have as yes, I change the position and the gain, because when you change the, of course, here, okay.
Cesar, let's give the audience a little bit of an idea of where you are and what the light pollution level is where you are.
Is the most highest number that you can imagine. I can see only at naked eyes, no more that, oh, sorry, too much. No more than 7 stars, really.
That's it.
9.9.
And one of those stars is the moon? I'm kidding.
Yeah.
Okay, 8.
Yes. You can see
oh,
the shape.
That's cool. You can get the planets and the moon, of course, but
yes.
But only
the
7
level of
stars.
stars.
That's like downtown New York or
yes,
maybe even
the
Las
same.
Vegas, you know. So
absolutely. And now we are watching, and it's incredible, really, to have this kind of image. Yes, I prefer here with more gain. Oh, sorry. This is light pollution because here you can see the shape, like this is the something like you can imagine, like the legs of the tarantula. You know that this is a non-processed image. This is a single view of the nebula. This is something magic. This is something similar when you watch the nebula here in the city, or maybe not in the city, maybe in a more rural areas with more with less light pollution, where you can see the same size, the same details. Sorry, not size of the nebula, but it's difficult now to me put the right number to show to the people more details, because the nebula is lower in the horizon, you know. But if you like, we can try in few minutes. I don't know how many times I talk in my presentation, but maybe in 5 now we can process a first level image that I took, the last image that I took, if you like. We need to change this.
I think you probably have some final images that you've processed. And you know, you might show those just to give an idea of what is possible from you know, doing astronomy from your balcony.
Absolutely, and it's something that we can share now. Okay, now I'll open. Yes, maybe in 5 minutes we can process very fast image to see the final image. Something that I use here. Okay. Well, I share. Okay, and I'll share again.
We can see his telescope back there. He's got an
yes,
Explore Scientific IXOS 100 and ED80 refractor.
Yes.
What's that on top? What do you have on top of the telescope?
Now I don't use that. That is my mini guider telescope.
Auto guider.
Today, you don't need more than a small telescope for guiding, and it's a beautiful time for astronomy. Here you can see the camera.
Yes.
You see the camera. The second camera that I don't use now, and the mini guider. All is very easy you
Yeah.
can, for the people, sometimes the people think that it's impossible, but this is a entry level, very good mount, very
Mhm.
easy to carry in your plane. And if you take a trip in the plane, this telescope is so small like this. When you fold, it's like something for very short, and you can put in your pad bag. It's
Yep.
really fun. If
That's
you
cool.
like, I try to make a very
Okay.
fast process now.
Let's see a quick processing of a single frame.
Yes, yes, of course, because it's a single frame. It's easy, it's fast.
This is so gratifying too, because as Caesar said, he can't see more than, as he said, about 7 stars up in the sky. And a
Yes,
setup like this, if you're in the city all the time and you love astronomy, to be able to get out and to, it's like lifting a curtain away, to be able to see deep sky objects through your telescope with even a relatively modest setup like what Caesar has, but with all the computer technology that we have today, the software and filters and all the rest of it, you can do some amazing work from the city.
yes. I need to know. No, it's not. Okay. Oh my. Maybe. I don't know
Some people
why
are
I have
asking,
a.
Caesar,
Yes, yes. Tell me.
is that nebula in another galaxy? Was this a nebula in
Yes,
one of
it's
the
in another
Magellanic?
galaxy.
Another
Yes,
galaxy.
yes,
There you go.
yes.
It's the tarantula, right?
Tarantula Nebula. Yes,
Yeah, it's
Tarantula
a
Nebula.
huge, huge nebula.
Absolutely. Yes. I don't know why. Okay. So
You'll find it.
yes, I don't know because maybe we change where I tried. If not, captures. Okay.
Yeah, this is in the Large Magellanic Cloud. Um, and it was discovered by Nicholas Louis de Lacaille. I think I'm pronouncing that correctly. During an
This is
expedition to the
great.
Cape of Good Hope between 1751 and 1753. He cataloged it as the second of the nebula of the first class. It's nice. Which are nebulosities not accompanied by any star visible in the telescope of 2 feet. Okay. Well, I think you're going to see, even in this 80 millimeter scope, you're going to see some stars here. The distance, let's see if we have a distance for some nebula. They have a tough time measuring distance. I'm
processing all that I can.
Okay.
Let me. Okay. I need to stop here. Okay. Start. Okay. Here we have. Section. Okay. I don't know.
The distance to Earth of the
Okay.
Tarantula Nebula is roughly 160,000 light years away.
I'm trying. Normally, the livestock, the livestocking, what do you say, are here. Okay. Well, here we have in 3 different colors. I'm starting with this.
Oh, wow. There it is. And this is just, how
Maybe we
long is
can
this
try,
exposure?
yes.
How long is your exposure?
14 minutes was
14 minutes.
yes.
Okay.
We try to color calibration with
And how about the camera? What kind of camera are you using?
the camera is a Symony 605. It's a camera with a square sensor, 3000 by 3000 color sensor. The size of the each pixel is 3.7 microns.
So John Ray is watching on Facebook. He says, this is fun. Global Star Party is evolving into an online astronomy science magazine. Great stuff.
Yeah.
Thank you,
Wow.
John. Thank you. Well, it's cool. I mean, we got, we have live images from around the world here. All of us in the Northern Hemisphere, many of us have never seen the Magellanic Clouds, so.
Yes, it's in very dark areas are really, now I'm using plate salt to find the, yes, 30 dorado cluster, if that's possible.
These are all techniques that would have been so difficult to do in the 80s and the 90s.
Yes, when we use films, this is incredible. Now,
And
yes,
then
we are developing in a live developing. I try.
Yes.
I choose the red color, the red channel.
Okay.
The people can see all my my. Wow. Yeah. The most fun thing is that I have the bar of the presentation of the Zoom and
right
now. Okay. Yeah. Sorry. Perfect. Well, it's not a perfect process for tonight, but maybe.
Yeah, but look at all the stars. Oh, and is this nebulosity?
We are going.
Okay.
Yes, more nebulosity. Yes, of course that it's not perfect.
And this is just one frame. One frame. Okay.
Yes, it's one frame or it's a live stacking of a single 5.
Some nice
well,
comments
sorry
here.
by this, but here do you have more details?
Yes.
I will show you very fast a better picture of this. I'll change to my presentation very, very fast. And I'll show you how a picture that I took yesterday
Okay.
of the same nebula, but it's not perfect, but maybe you have a much better, you know, view of the nebula.
So you're getting some nice comments here, Caesar. Jeff Wise claims
What?
that you have Bortle 12 skies. Is that possible?
Yes, it's possible.
Maybe
And
during the daytime.
you are watching that. It's possible. Well,
Yes.
here I this is the presentation that I have prepared did this of if we was having to have a
If you didn't have
yes.
clear skies. Okay.
Yes,
Okay.
very fast.
All right, let's
The
quickly go
pictures.
through this.
Yes, the pictures of Catamarca 2 months ago, Catamarca Star Party. Here you can see this is dust in the floating because we had a very, very strong winds in the day, but the night was really great, but with a very bottle tree, but with a lot of dust floating in the air. We have a great time, more than 80 people in Catamarca en el Rodeo. We have a special work with EXS 100 mounts using with Nina. We make a great, we have fun with this here with the people here. My telescope in Catamarca.
Cool.
The Explore Scientific equipment. More people, the Explore Scientific corner.
Very nice.
We have the eclipse. We was really happy enjoying the partial eclipse in Catamarca. We gave to the people materials, solar shades to make filter for telescopes and solar sunglasses for every participant. Really, we enjoy a lot the solar eclipse. The people making their own filters because we make a special introductor and a special working in filters. Here, our customers, our friends.
Very vibrant astronomical community down there.
Yeah, absolutely. Really, we enjoy a beautiful place with our friends. Really, it was a great safari. Here to have Orion in opposite side.
Oh, that's right. It's upside down.
Yes. Remember this if you came here. More pictures, all with cell phones. We don't use more reflex camera to take pictures of the people of the star party. It's incredible. Yes,
that's great. It's great.
It's great. Yes.
The cell
Here,
phones,
the name of this is
smartphones are getting so
smartphone
much
incredible.
better
This
for
is,
this kind of thing.
Absolutely. Right? This is here Scorpius, and here is the southern. Well, I don't remember the name of this, but for the next in English I don't remember. But this in Northern Hemisphere you have something similar. Our friend Gabriel Bengochea, he's physics in one of the talks. They're very great talks. And a picture that was not the idea to take this picture, but was great. It's not a great picture, but was only to use. Yes, in the
Yeah.
In the workshop of Nina and EXUS 100, we take this only for try, and was a great experience. And this is my the picture of the eclipse from Catamarca. And another galaxy, well, this is something that last third party I can participate, because I supported to people that they needed to take takes more takes of a filmation of filming of a documentary. And this was in my backyard, in my building, my tower where I live. Well, we are making all these kind of praises thing, and of course that something that we had a very, very bad rainy day, and these guys, Alejandro, make these spheres of moon, planets, and this was a part that of the documentary of people that are teaching in astronomy in Argentina. Of course, that in our third parties, never do you use umbrellas, but you know, this was the condition for this fake star party. But finally, we see the moon. This is Jaime Garcia, my friend, that they came to Buenos Aires, and we say, okay, we can take this few takes of the filming, because we are together, and we you know, we need to complete for these people that they need more takes of the filming. O sea, the idea is that this is not in my backyard. If not, we told to the people that this is still in our Valle Grande Star Party in Mendoza.
I see.
Yes.
Well, that's Hollywood
but finally,
special effects. So.
Yes, but finally this is real. yes, you know, and this is real because we found the moon in a hole between the clouds.
Good.
Yes, the fake star party finally was a small real star party in the end. It was very, very fun with the filming team, and to get people that normally we are customers and friends that came here to my home. And well, this is my setup that is the same that I have now. And this weekend, I took a picture with the same equipment of the sunspots that tonight, this week is really, really strong, the solar activity. For all people that are interested in take pictures of the sun, use a safe solar filter.
Yes.
And with a very, very cheap telescope, a safe solar filter that are not expensive, you can get a great pictures using your smartphone. Look the details, sorry. This is with the same equipment, with solar filter, with the same.
Wow, look at all the sunspots.
Yes, great. Yes, sunspot with the same telescope, same mount. Yes. This was very great because my father was with me. My father have 85 years old, and actually is really every time more interested, and I give him a new telescope, and is really happy. He's made his own mount, totally inspired in a azimuth mount, like a nano azimuth explore scientific mount, because he
similar
he
to
told
that
me,
design. That's
yes,
cool.
yes. Next week I will show you a picture. Well, here it is more. It's a picture of yesterday.
Yeah.
With the.
And this is from your balcony, right?
Yes, absolutely. Here you have a more complete. I prepare a more complete picture, a well processed picture for next week, because I prepare another picture especially for
Okay.
to show to the audience of this nebula, because I have more material to process. But this is a very, very fast process that only to show the shape of the nebula.
Right.
Well, here is very interesting because I use it from here and a small planetarium camera to Orion from not from the balcony, if not from the rooftop. And I took this picture of Orion, but with a planetary camera. It's very interesting because
it's very
sometimes
narrow field. Yeah.
Yes, very cheap planetary camera.
Yeah,
This is very important. Yes.
Wonderful. Caesar, thank you.
Well, thank you. Sorry about the time, because Robert is a white to.
He is waiting. That's right.
Hi, Robert. How are you?
We're going to bring him on right now. That's right.
Doing good.
Yeah.
Yeah.
Yes, I'm ready to enjoy the Robert with incredible
lunar
pictures. Yeah.
That's right. That's right. That's wonderful. That's
Well,
great.
thank you very much.
Caesar, thank you. Thank you for coming on.
Thank you very much to the audience.
All right.
And it's a pleasure to share the sky with the people.
Yeah, wonderful. Wonderful. Okay. Robert Reeves is a world-renowned astrophotographer and lunar photographer. He is, I think he probably knows more about the, intimately understands and the dynamics of what goes on with the moon and knows the terrain like no one else. So there's got to be, I don't know, Robert, I think maybe there's only a handful of people that might understand it as well as you do. There was a comment kind of leading in that similar vein there. John Ray is watching on Facebook, and he said, Caesar makes me wonder, in the statistical sense, what percentage of the human population is as aware of astronomy as we are? And he's talking about all the amateur astronomers that would be watching right now. I read many years ago that only 1% of the human population had ever knowingly observed the planet Mercury. What do you think about that, Robert?
Well, I've heard that statistic as well, and I think it's very believable because Mercury just doesn't stand out like Venus. It's not in your face, or it doesn't have the intrigue that Mars does. When Mars is up, it gets a little bit of press, but Mercury pops up every couple of months and then ducks into the morning sky and comes back and kind of seesaws back and forth, and really doesn't have a good press agent because it's so insignificant.
Needs some marketing.
It does. It does. But I'm glad to be here tonight. I was racing across the state of Texas to get back here in time. Got home while John Goss was halfway through his, and threw together probably my most disorganized presentation yet, because I just barely got here in time. Chasing across the state of Texas to pick up another load of those lunar orbiter pictures.
Wow. Okay.
Yeah, the back seat of my F-150 is stuffed with hundreds of lunar orbiter pictures.
Oh my goodness.
I haven't even had time to bring them in yet. So it's going to be an interesting week as I sort those out. But in the meantime, I think the theme of your presentation is the age of the universe.
Well, yes, sir. Yes,
the
sir.
age...
You said that the moon is a great stage to talk about the age of the universe.
Yeah, a little bit of a yardstick, because we can see it. We can look up with our own eyes.
Sure.
And the moon is just a little bit older than this, just a little bit younger than the solar system. The moon was formed, probably 100, 150, million years after the solar system. So it's been around almost as long as our solar system. So that yardstick is about 1/3 the known age of the universe.
Okay.
About 4.6 million years for our solar system. The universe, 3.2 billion years, I think, is the figure kicked around. So about 1/3 the age of the of the universe, we can look up and see an object with our own eyes, the rising full moon, and see features on it that are almost 4 billion years old. And we can see that with our own eyes. So we can look up and see something that's been around for 1/3 the age of the universe as we know it. So the grand experiment, and go to screen share and see what happens here.
Okay.
And are we seeing my postcards from the moon?
Yes, we are.
Hey,
Perfect. Perfect.
alrighty, boom. So, moving on. Come on, it's not advancing. We're going to do this the old-fashioned way. There we go. Ages of things on the moon. Now, yeah, we'll acknowledge that the moon is only 1/3 the age of the known age of the universe. So we'll deal just within that narrow time frame. But most of us, when we were kids interested in science, we also had this fascination with dinosaurs. And we heard these terms like Jurassic and Triassic and Cretaceous, these epochs of time in Earth geology where various things happen. And that's how paleontologists, divide up time as to what happened way back when. Well, the moon has similar epochs of time, and we categorize things on the moon in this manner. The pre-Nectarian epoch was from almost 4 billion years ago back to the formation of the moon, almost 4.5 billion years ago. So anything that happened on the moon in the pre-Nectarian epoch is truly ancient. It is some of the original features on the moon. The Nectarian epoch, very brief, only 100 million years. This is during the late heavy bombardment when Jupiter and Saturn entered a 2-to-1 gravitational resonance and shook up the solar system. It dusted the inner planets with thousands of asteroids and comets that were dislodged by this gravitational interaction between the giant planets. Eventually, Jupiter and Saturn, their orbits shifted. They're now not in that 2-to-1 resonance, which is a darn good thing. Otherwise, we wouldn't be here. We wouldn't be surviving the continuous impact of all of these asteroids and comets that would be thrown into the inner solar system. But during this brief period of time, the giant basins were formed on the moon. Now, we can see these with our own eye. When we look, this picture of the full moon we see here, we see part of the face of the caricature of the man in the moon. These dark regions, the Maria, the lava that is filling up these giant basins on the moon. The basins themselves are almost 4 billion years old. So you can look up and watch the full moon rising above the horizon and look at this very romantic scene, but realize the science behind the creation of this almost at the way back near the beginning of our solar system. The next epoch was the Imbrian epoch, from about 3.85 to almost 3 billion years ago. This was when heavy volcanism was on the moon, and it filled in these basins with dark basalt and paved them over and created the dark areas that make the caricature of the man in the moon. Now, I'll slide here in a second. I'll make an effort to differentiate that the basins that the Maria lie in and the basalt that makes the Maria are two different features, but we'll deal with that in a moment. Then we entered a rather lengthy, almost 2 billion year-long epoch, the Eratosthenian epoch. This is where a lot of the post-Mare formation cratering occurred on the moon, a period of almost 2 billion years. And then getting up to the current epoch, the Copernican epoch, from about 1 billion years ago to the present. And during this time, the impact rate on the moon significantly reduced, and perhaps by a factor of 300 over the earlier epochs. And any crater formed during this Copernican epoch, we could tell it's fairly young because it still has the crater rays radiating out from it, like we see on Tycho or Copernicus. So let's advance the slide. Oh, it's working now. And look at a representation by Don Davis astronomical artist Don Davis of what the Nectarian epoch moon looked like. This is the early moon prior to the volcanism that altered its face and created the Maria. We see the giant basins, the one on the top, the Imbrium Basin, over on the extreme right, the Crisium Basin. All of these basins, well, not all of them, take that back. There's something like 70 basins on the moon, but only the low-lying ones on the near side filled with basalt, and we can see them now as the character of the man on the moon. And I've been gone all day long, and my cat is being very persnickety about wanting to get into my lap. So if you see a cat poking into the field of view, that is Tinker.
Yeah. Pets are allowed on global
Yeah,
scale.
unless they try and walk across the keyboard like she's trying to do. So
we'll take control of the presentation.
So we move on a little bit into the Imbrian epoch. Like I said, about 3.85 billion years ago to a little over 3 billion years ago. And this is when the Mare forming volcanism occurred. And kind of made the moon look like it does today, but there's a number of significant landmarks still missing. Come on, cats, stay off the keyboard. So we get up to the Copernican epoch, jumping over the Eratosthenian. This is from about 1 billion years ago to the present, and now we see the moon has a little more personality. The rayed craters, Tycho and Copernicus are seen, and many others as well, but they're too small to be seen in the detail of this small painting. So we get down to the basics of it. All of these features on the moon from 4 billion years ago up to today are only formed by two different basic landscape forming processes, either an impact by a meteor or an asteroid, or subsequent volcanic modification of the impact. Case in point, the Maria themselves cradled in these basins. Here in this full moon image, if you back off enough, you can begin to see the caricature of the man on the moon, Imbrium making his left eye, the combined Serenitatis and Tranquillitatis forming his right eye, Vaporum in the middle making his nose, Humorum and Nectaris, no, I mean not Nectaris, getting brain locked from too much driving today. Anyway, the sea of humidity and the sea of clouds down in the lower left kind of form his offset smile. So these dark Maria lying in basins, the basins almost 4 billion years old. The Maria within them almost 3 billion years old. So then we move on, and like I said, the basins and the Maria laying within them, two different features formed at two different periods of time. Now, like I said, the Maria define the face of the moon and create the caricature of the man in the moon. There's 21 of these on the near side of the moon named Maria. 11 were named by Giovanni Riccioli back in the 17th century, and the moon kind of stayed static for about 200 years. And then in the 19th and early 20th centuries, 8 more were named. And then during the space age, just in recent, during our lifetime, yours and mine, 2 more Maria were named. The last one, Mare Insularum, between Copernicus and Kepler crater, named in 1976. So fairly recent. Now, mountains on the moon. We tend to think of terrestrial mountains as kind of impermanent. I mean, they look imposing, they look very pretty, but as geologists, we know they're not going to be around long. Earthly mountains will either erode or be altered by changing plate tectonics, subduction, land masses pulled back under, melted in the interior, and new mountain ranges build up with the collision of crustal plates. This is a process where earthly mountains are continuously destroyed and for various reasons and continuously created. But when we look at the moon, lunar mountains have been frozen in time for almost 4 billion years. Lunar mountains like the Alps here, the Caucasus Mountains on eastern Mare Imbrium, all mountain ranges on the moon, are named after terrestrial mountains. The Apennines here, pointing down toward Eratosthenes crater, the Carpathian Mountains just above Copernicus. These are all the outer rim of the Imbrium impact basin. So these mountains were formed almost 4 billion years ago, and they have been unchanged since. Unlike Earth mountains that have come and gone many times, these stand pretty much forever. Now, jumping up to about 1 billion years ago or less, we can tell the craters on the moon that are fairly new, less than 1 billion years, because they still retain their ray structure. All craters create a ray structure upon impact. This is the splash of material thrown out in all directions by the explosion that creates the crater. But crater rays fade in time because the constant infall of meteoric material, solar radiation, coronal mass ejections, impacting or interacting directly with the lunar surface will eventually make crater rays fade. So after about 1 billion years, they're gone. So if we see craters with rays, they're fairly young, like Copernicus on the right-hand side, is a big splash, about 800 million years old. In the upper right, Aristarchus crater, a smaller ray pattern, but about 200 million years old. And if my slides are right, yes, here we go. Tycho, one of the few craters that, well, we can't see Tycho directly with the naked eye, but the ray structure at full moon, all the radiating rays point like an arrow to the middle where Tycho is. So we can see where this crater is because we can see this ray pattern with the naked eye. But this one, only 108 million years old. This is dated by analysis of samples returned from the Apollo missions. Apollo didn't necessarily land anywhere near Tycho, but these impacts scatter material across the face of the moon. So when the astronauts selectively picked up various samples at the Apollo landing sites, they analyzed them very carefully back on Earth. We can backtrack a little bit and determine the gross origin of some of these things that were literally thrown across the moon. Mm. And again, just kind of backing off a little bit and realizing, when you go outside and see that beautiful full moon rising, I believe it's a full moon tonight. If it's cloudy here in Texas, so I've kind of lost track, but I think it's one.
A little bit past full right
okay.
now. But,
close enough.
But still, yeah, it's the last few days have just been beautiful. And
yeah,
this morning I took pictures of the moon just in the blue sky with my iPhone, and it's just it's beautiful. I love that when the sky goes from like a little pink to that blue color, and the moon just out there. It's just
it's just standing there like a neon sign, kind of like this
yeah.
image. So when you look at it, look at those the bright southern region near Tycho. These are the southern highlands. These areas are basically pre-Nectarian. They date back to the formation of the moon, almost 4.5 billion years ago, and then progress up to look at the Maria, formed a little over 3 billion years ago, and then continue your scan, Copernicus crater, nearly 1 billion years ago, and then Tycho, only a little over 100 million years ago. So you can see with your eye features that span virtually the entire age of our solar system. And you can do this almost with your naked eye, and certainly with a pair of binoculars. No telescope needed to enjoy these basic features that span the time scale of the universe, or the solar system, I mean. just quickly go through again some to wrap this up. Features the Alps Mountain Plateau crater, basically around 3 billion years old, jumping up to Tycho crater, the youngster, very young, only 100 and, oops, what happened here? Only 108 million years old. Aristarchus crater, about 200 million years old. Youngsters. A scene across the northeast, Atlas and Hercules crater in the foreground. Eratosthenian epoch, up to about 3 billion years old, going out toward the horizon, Mare Humboldtianum on the horizon, the very large, broad Mare up there. The Humboldtianum basin formed almost 4 billion years ago, and the lava flows in it a little younger, almost 3 billion. So we get a whole time scale across here, and the beautiful ray structure around Copernicus, just scattered out in all directions. Just mesmerizing when you look at this in a telescope.
It's mesmerizing right now.
And back to the youngster Copernicus, excuse me, the youngster Tycho, and we see it as nested in between some other larger craters below it. These craters are almost 4 billion years old. So Tycho is laying in this crater field that is 40 times older than it is. A little over 100 million years for Tycho to over 4 billion years old for these massive ruined craters in the same neighborhood. So, concluding, I like to say the moon is not a graveyard for dead philosophers and scientists. We've got the names of our scientific elite immortalized on the moon, but the moon is a dynamic world filled with wonders and scientific delights if you just take the time to look. The moon is available for viewing most of the month. The moon does not require a dark sky. The moon laughs at light pollution. It doesn't care. You can see the moon from the brightest locations. And it's the only celestial body that humans have explored in person, and through a telescope we can see details as small as a kilometer on the moon. It's the only world we can get that kind of detail. So there's much to love on the moon, and I dearly ask that you all come out and play with me on my playground. So it's been fun, and hope to see you next week.
Yeah, wonderful. Great presentation, Robert. That's awesome. You also, I don't think you mentioned your book, but
well, I
the
can.
people in the audience have been mentioning it, and I think many of them will be buying that book. So,
well, I hope so. It's if you're interested in the moon, it's 300 pages, 422 illustrations, non-technical. It will take the lunar novice up to a lunar authority without needing to know geology or math, no chemistry. It's just the moon, as I explained it, very similar on our presentations here. Exploring the Moon with Robert Reeves. My name is in the title specifically to differentiate it from the many other books also titled Exploring the Moon.
okay.
And do a title search on Amazon, and boom, there it is. Order it. It'll be on your doorstep in 2 days.
Yep. So you have a link there, whatever channel you're watching on right now, and you can definitely get your copy. So, Robert, thanks again, and I hope you're not burying yourself under too many historical lunar photos.
Well, it's a real fun journey. I almost didn't make it back in time because the people I was getting them from, they weren't that up on the history of it and exactly what they were. And before I know it, there's this whole audience just pouring over them as I'm explaining them. And it took me a while to get out and then drive like heck to get back across the state to get back here in time for tonight.
Sure.
But it's been
But
a
you're
real
saving
trip.
these very historical images, and I think that's wonderful. I would invite you, if you're so inclined, to write an article about it for Skies Up magazine.
I sure
And
will. I saw
yeah,
your note, and I'm going to do that for you. And
great,
so
wonderful. Okay.
next
Well,
week
thank you
we'll see
so
you.
much, and have a good night, Robert.
You
And
bet.
yeah, he keeps inspiring us to look at the moon, and I think it's just wonderful. Our last speaker for the first segment of Glory Party, Breacher Ronald, the Astro Doc. He is one of the masters Pix Insight, and he's an incredible astrophotographer. I get in my inbox frequently wonderful images of galaxies and nebula that he's done with his rigs. So thank you for coming on to Global Star Party again, Ron.
Oh, thanks for having me, Scott. I've been traveling like a wild thing, so I missed the last couple.
Right.
And last week I was teaching.
Yeah, you're teaching astrophotography, right? Yep.
So, but I really love doing these things because I always look at your themes and they make me think in ways that I might not otherwise think.
So, oh, that's great. That's great.
Very cool.
Well, wonderful. Now I have David Levy, who will be working with me to further develop some of these themes. And, he's such with all the books and all the events and lectures that the man has done, it's just, it's great to have him at arm's length as just a friend, but now to kind of work with him together on this thing is going to be really cool. So.
That's awesome.
I will let you take it away.
All right. Well, let me share my screen with you and switch to my slideshow. Can you see the slide just fine?
Yes, I can in presentation mode. Yeah.
So in all of these presentations, like I said, I try to somehow work with what I love to do, which is astrophotography as well as visual observing. And weave it in with the themes that you come up with, Scott. So tonight I'm going to just talk about Bok globules in my image, and there's a couple of circled on this title slide, but we'll get into that in a minute. The inspiration for this talk is Jan Bok. He was more commonly known as Bart. And he passed away in 1983 after a long career as an astronomer and teacher, lecturer. He was a Dutch American, and he was best known for his research on the evolution and structure of our home galaxy, the Milky Way galaxy, and for the discovery of Bok globules. And so I thought it would be fun to, first of all, look at what Bok globules are. And then second of all, where are they in my images? Because I've taken hundreds of images of regions that ought to contain Bok globules. So let's see what we can find. Now, I come on this fairly often, and I don't show these slides every time, but I always get people trying to get in touch with me afterwards. So this is just so you know who I am. I love to write and teach, and two of the things that I'm most chuffed about lately is I'm now a contributing editor for Sky and Telescope magazine. And, just 5 or 10 years ago, I was reading that magazine just, it was my go-to magazine with Astronomy magazine. Now I'm writing for it. That's really cool. And the Pix Insight folks have identified me as a Pix Insight ambassador, which means that they have confidence in the way I'm teaching Pix Insight. So that makes me feel good too. And you can see how good I feel because this is a picture of me in a happy moment in my observatory with a bottle of cider, which my daughter calls wobbly pop. So what are Bok globules? Well, they're dark structures that contain dense gas and dust. Now, in an image like this, there's lots of dark structures, of course, but there's the Bok globule. They're isolated dark structures. They're quite small, typically around 1 light year across, sometimes bigger, sometimes smaller, and having about 10, the mass of about 10 suns. They tend to be found within H2 regions. H2 regions are generally emission nebulae that are dominated by hydrogen, which gives them this natural pink sort of color. And this image shows the Pac-Man Nebula It's probably the first thing most astrophotographers image that contains a Bok globule, because it's a really popular target, very well placed for northern observers to shoot. And there's that Bok globule shown up close. It was first suggested by Bart Bok in the 1940s that these globules were star birthplaces. And he described them as being like insect cocoons. Now, of course, in those days, they were working just with visible light, and it's hard to tell what's going on in an area that by definition is dark in visible light. So it wasn't actually until about 50 years later in the 1990s that that it was confirmed that these Bok globules were birthplaces of stars. So I went through a whole bunch of my images to look for Bok globules. Now, I'm going to say I did my very, very best to confirm that what I'm going to show you are all Bok globules. But I couldn't confirm that. Sometimes the literature just referred to them as globules, but they sure look like it. And if I'm wrong, sue me. They're still beautiful to look at. So this is the Rosette Nebula. It's about 5,200 light years away. And you can see there's a beautiful star cluster at the center. But just above the central donut hole, there's all these isolated dark structures. And particularly the one that's below right of center, I think, is a Bok globule. But you see there's also some up here on the far left of the image as well. This is the Pillars of Creation. Very, very famous. It's a part of the Eagle Nebula. This image was made by me combining some color data that I had with some narrowband data from Pete Prue, one of my partners at Masters of Pix Insight. This structure is about 7,000 light years away. And the height of these pillars is around 90 trillion kilometers. That's a 90 followed by 12 zeros.
Wow.
That's a big
That's a big number. That's hard to wrap your head around.
Yeah. And, you know, it's easy to miss these things while you're looking at the Pillars of Creation. But if you look off to the right, under the 90 here, you'll see another beautiful Bok globule. This is IC 1396. It's a really large emission nebula. This image was taken just about a month or two ago with a very small telescope, actually a 60 millimeter refractor. Remember that for photographing large things, you need a small telescope. And you can see all the very cool dark structures here, some of which are Bok globules. But I want to highlight for you within this image, this region here. This is known as the Elephant Trunk Nebula, and there it is there. And this again is a very famous globule. I couldn't verify this was a Bok globule. It's referred to as a globule here, also known as Vandenberg 142. And it shows very, very cool structure. So cool that I thought I would blow it up for you one more time so that you can see all the beautiful color and texture here in the eye of this elephant trunk. This is one of the first images that I shot with a color camera for deep sky photography. This is the Lagoon Nebula, Messier 8. And the Messier designation actually refers to the star cluster that you see, the bright stars just left of center. But you can see this structure also shows a ton of isolated dark globules these Bach globules that might be star factories. And here's another favorite of mine. This is the Tadpole Nebula, IC 410. It's in Auriga, and it's well placed right now for imaging if you want to image this. Again, you can see all sorts of isolated black structures. Unfortunately, to my eye, the most interesting part of this image of the tadpoles, that's these structures to the lower left of center. They're also star factories. It's thought that there are new stars being created at the heads of the tadpoles. And they're about 10 light years in length. That's huge. But that also gives you an estimate of the size of that dark structure in the upper right. It looks also to be maybe about 7 to 10 light years across. And this object is 12,000 light years away from us. You notice that all the structures I've been talking about are in the thousands of light years. That's because the Bach globules were discovered, as far as I know, all of them were discovered within our own galaxy. That was what Bart Bach was most interested in studying. And in distant galaxies, it's tough enough to see the emission nebulae, let alone small dark structures within them. So all of these are in the thousands or tens of thousands of light years, not the millions of light years that galaxies would be from Earth. All of the Bach globules that I've shown you so far have been in bright red emission nebula, emissions from glowing hydrogen. But there's a few Bach globules, and this is one of them, that are present in dark nebula or reflection nebula. So this region here, the blue nebula at the far right is Vandenberg 152, and the dark tube snake-like structure that goes through the image is a Linz dark nebula. I'm not sure what the catalog number is, but joining them is this dark structure, which is identified as a Bach globule. So this is an example of a Bach globule in a region that is not a bright red emission nebula. And here's another one. This is the dark shark nebula. You can see the shape of the shark. And it's only 650 light years away, this dark structure. But look at the eye here,
Wow.
or the
That's
snout.
cool. Yeah.
How
mouth
isolated.
is open.
Yeah, mouth is open, ready to strike. He's got a dorsal fin, and he's got these lateral fins and a nice tail. And I don't know if you can see it, but right here, there's a little galaxy that's in the far, far distance.
Oh, yeah.
Yeah, and all
Yes.
these beautiful reflection nebulas. So if you go to my website, and which is astrodoc.ca, and you search for dark shark, you'll get a high resolution view of this where you can zoom in and see that little galaxy up close. It shows some cool structure. So I guess I want to close. I'll stop my share and close, Scott, by thanking you for inviting me to think outside the
Yeah, well, thank you.
outside the
Thank
box.
you. Yeah, your images are filled with Bach globules. So
Yeah, they are, and it
I
was
think
really
that's great.
fun. And Dan Higgins is asking me privately in the chat whether I cut my hair. And no, I did not cut my hair. I just washed it.
Okay. Later, it'll just poof out. And
Poof,
that's
yeah,
cool.
it'll go out later.
That's right. That's
Anyway,
right.
Scott, thank you very much again for having me.
Thank you so much. Thanks, Ron.
Okay. See ya.
Okay, so we are going to take a little break for a few minutes, and we'll be back with Marcello Souza. We've got Marcello Souza coming on, Dan Higgins from Masterworld TV, Adrian Bradley, and John Schwartz. So hope you're enjoying the 137th Global Star Party, and more to come.
Really quick, Robert, I wanted to apologize to you in person. I could not remember your segment on the beautiful pictures of the moon and your explanations last week. I was trying and I couldn't think of it. But so I think I said something like moon stuff. So it is definitely not just moon stuff. It is there's you show a lot of detail and give us a lot of things to search for should we want to observe the moon. So I wanted to correct that on Global Star Party.
Vai dormir, cara. Você já estudou, fez sua parte. Vem cá, vai. Não tem nada não, cara. Tem meu celular aí pra mim? Aonde? Eu preciso dele. Tem meu celular. Hidratação requer o que é isso? Eu estava vendo aí no comentário que tem muitos bonecos que falam de madrugada. Muitos que vão falar de madrugada, estou fazendo espera. Não, mas aí você está contando, tirou filho, joga fora, né? A moça começou a falar com ele na madrugada. Ela conseguiu um desespero. Vários relatos. Vou começar daqui a pouco. De boneco começa a falar de madrugada.
Yeah, by the way, I'm seeing the chat. We've got some pretty good moon stuff going on. It's clear up here. It's also cold.
How long? I'm scrambled, but I got it. Need your help. You address? Jeff, that would be so fun to cruise and do all the major star party if you're gonna rock it.
Okay, we are back. Hope you enjoyed that little break there. And we've had a fantastic global star party so far. Of course, starting off with David Levy and introducing Bart Bach, who gave his lecture on the age of the universe. If you're just now kind of tuning into Global Star Party, you're going to want to watch this after the broadcast, the live broadcast, so that you can
And the
see this segment because it's
$5,000.
really fantastic. David Eicher also gave commentary about Bach's, then 1957 estimates or information about the age of the universe. So what was interesting is that basically Bach was giving all the right information, but the numbers have been just revised about 20% or so. Janet Ivy Densing gave a fantastic presentation. Her focus is on youth in science and astronomy, and she just does an amazing job. Her passion and energy and ideas about how to teach astronomy to young people. Actually, I was learning some stuff there, so I guess I'm still young. John Goss from the Astronomical League was on. Cesar Brolo had a clear night from his balcony and getting the Tarantula Nebula. Robert Reeves dashing in from collecting some historical lunar photographs and gave a flawless postcards from the moon presentation. Ronald Breacher with following on with inspiration from Bart Bach and Bach globules in his images. So up next is Marcello Souza. Marcello is the founder, I believe, and president of the Louis Cruels Astronomy Club. He is a professor of astronomy, a cosmologist, a physics professor, an amazing outreach, educational outreach force in the Southern Hemisphere. And he is the editor of Skies Up magazine, and he's a good friend. And so we're very happy to have you on. You are just about as regular as anyone on Global Star Party. And Marcello, I really appreciate you devoting as much time to it as you do. And also for all the time that you devote to collecting articles from around the world for Skies Up magazine. So I'm very excited to learn what's going to be in the next issue.
Hi, nice to be here. Thank you very much for the invitation, Scott. Thank you for the kind words. I hope that in December we are going to have a new edition of Skies Up. It's almost gone. Have many artists that are arriving.
Yes.
And it will be a fantastic new magazine. If anyone wants to send the contributions, you'll be very welcome.
Yes.
You
That's
have
right.
you analyze the contributions and you'll be welcome. Today I prepare a presentation. First, I will show what we are doing here. We are organizing many outreach activities. Here we are arriving in summer. On a moment that I will share my screen here, but okay, I hope it will work. On a moment. Here, I think that it will work. Oh, okay, it's here. And I will show first what we did last week. We are developing a new project here that if everything will work well during the summer, we will have new activities. Hi, can you hear me? Hi?
Yes, we can hear you fine, Marcello.
Yes, because for me it's frozen here. Let me see if my computer helped me today. On a moment, but I will talk about it, before I can change the screen. Now it's okay. It's working for me now. Something is not okay, but I will stop share again. In a moment. Sorry, but my computer sometimes.
Sometimes, yes, we all get these sometimes. Me too.
Now what's happening? I'm trying to change the screen, but it's not working. On a moment, I'll try again. Here's correct one. Okay, now I think that's it. Where?
Yeah, you just need to bring it into presentation mode.
Yes,
You can see your PowerPoint.
Yes, I'll do again.
Okay.
I will leave the presentation mode and I'll try again. I know what it is because some problems with the Microsoft's PowerPoint. Only a moment, Scott. Sorry for
No
this.
problem. No problem.
I hope one moment it will work. Let me try again. Well, yes, it's here. Well, let me. No, I don't know why this is happening. If it didn't work, I share it here. But I'll try. I will close the PowerPoint and open again.
Okay.
But I will say what we did because this week for us we are planning new activities this week because for us this week we have the opportunity to see the sun overhead. We have it 2 times per year because we are between the
Directly
tropics.
overhead. Okay.
Yes, direct overhead, and we don't have shadows. Only 2 days per week. For us, it will be tomorrow, November 29 is tomorrow, 30, Thursday, and also in January. We have another opportunity to see this during the noon and the solar. And let me wait here. The PowerPoint be okay, and this will happen. Okay, it is open. Everything is here. Let me try again. I hope this time it will work. Let me see. Oh. Is here. And let me be if you'll be fixed. I don't know why. It's not working. But I will try here to do something different here. One moment,
Okay. Yeah, you can see the slide. You can see it.
Yes, the slide?
You can see it. It's not in presentation
Yeah.
mode, but you can see it. Yes.
Yeah, it's okay. I will move here something different here in PowerPoint that will help me to show better. I'll do this. I don't need to use this space here. I'll bring it bigger here, and I'll try to. Something it's not allowing me to work with the PowerPoint. I don't know what's happening. First time that this is happening for me.
So Dan Higgins says try hitting the F5 key to see if it goes into the presentation mode. Oh,
it's
good.
working now. This was the activity that you organized last week in one school, and it's something different from. Sorry.
We only see like a white
You can't
screen.
see the.
We do not see the slide at all now.
No.
No.
I can see here what's happening. Let me go again. Sorry.
No problem.
Let me try again. And now.
Perfect.
For
we
me,
got
it's
it.
working.
Perfect.
Yes. This was the. Let me see if I can change these slides. I don't know why I can't change the slides, but this was the presentation in one school that we did something different here in this school. But it's not. I know how I will do. You say that if you No. Now it's changed.
Yes.
Okay. Then we used a telescope, real-time image in a telescope in Hawaii at the school, in this moment. Then the student choose the galaxy that you take the pictures. It was the first time that we did this with a big public. It was the project of the Falks telescope, and we see the telescope moving and take the pictures live for the students of galaxies. Then we studied the galaxies in constellation of Leo. This was an opportunity that we had to organize. And after this, we talk about the sun, and you have the opportunity to organize a solar observation there. And this is in another place. We have 5 schools that visited this place, and we organize a special activity of solar observation with 100 kids there. And this was another amazing experience that we had. This having a presentation for them. And now, as what I said, for us, tomorrow here in campus, tomorrow no, Thursday, here in campus, we have the sun overhead, and we will not have shadows. And we now send information for many different cities here for them organize an activity at this moment, special moments, with the students to show them the moments that they don't see shadows. And the sun is very active now. And today we had a big solar flare. It's almost an X class. And we have another one that happened this week. And then we will have soon they will arrive here, the particles, and then you have auroras, probably in the south of the United States, probably because they are predicting that will be a strong CME that's coming, coronal mass ejection. Then the sun is very active. I don't know what will happen. This was this light flare. This light flare that was very strong in the direction of the Earth. I hope we will not have a Carrington event again, but the sun is very active.
Yes.
Now, as we are talking about the age of the universe, I'll talk very short about some curiosity about general relativity with some results. These are the original work published by Albert Einstein, written by Albert Einstein in Another de Physique. The first one about the general relativity. And what you have, sorry, that is in Portuguese, that is the difference, because now for us, force, the gravity is not a force, is only we are following the geometry or the topology of the space-time is a way to have to understand it this way, because you are not dealing with a flat surface, and when you are not dealing with a flat surface, the distance between 2 dots, it's not a straight line, it's a curved line, like in the surface of a planet, on the moon, on the earth. The distance of the last distance between 2 dots, it's a curve according to the geometry of the region that you are. And what we have now, that consider the universe as you have 4 coordinates. You have the space and time, then you have the space time, and the mass and energy can modify the geometry, the topology of the space time. This is a way, traditional way that we measure the distance between 2 dots in Euclidean geometry. That is x squared, y squared, z squared. Then now you have the distance between these 2 dots. But a different geometry, you need to define how that you can measure the distance of two dots. This is the equation that allow you to measure this. And the light ever cross these regions, and the distance follow the way that you need the smaller time, less time between the two dots. This is a rule, the rule of the nature. Then how that you understand this way, short way, you have two persons in an apple here. They don't know that the apple is curved. Then they have a challenge to walk parallel each, between each other ever. But what happened, they will meet in the top of the apple. As they don't know the curvature, they can imagine that a force that made them be closer. But we can see here that you don't have any kind of force. It's only because of the geometry of the region that they were walking make them to be closer. It's the same thing that you can imagine for the universe. What is happening? Then we have the Einstein equations. We have one part of the Einstein equation is the geometry of the space-time, and the other is the mass and the energy, and the mass and energy can change the this space-time like this. Then when what was a straight line, now it's not a straight line, and the light ever use the way that you need less time to go from one dot to another, from one region to another region. Then we have other results from, and one of the results is this: when the light pass near this one star, they change the direction, and when you look from, for example, from the Earth, you see the star in a different position. The effect of the gravity that was predicted by Einstein. But why I'm talking about this? This was a measure that they did. This was the prediction of Einstein. The measure happened here in Brazil. And if you have, for example, two galaxies very far from us, one galaxy in front of the other galaxy, the galaxy that is behind the light of this galaxy change direction in many different directions, and you see things like this. That's a gravity. The galaxy that is closer to us acts as a gravitational lens. Then happen this. Here is the cross of Einstein. The four images that you see here around the first one that's in the middle, they don't exist. They are images from from an object that is behind this one that's in the middle. Then you can see four different ones. Here is your Einstein ring. That is, if you have it exactly behind, then the light moved in the different directions around the one that's closer. Then you see a ring around this image. That is Einstein gravitational lens. But the universe is expanding as we see, as we know. And when the universe is expanding, the distance, the galaxies begin to be more distant. The distance grow between these galaxies. And Hubble was using the result from Vestor's leaf. The theory he proved that the galaxies that are very far from us, not in our local group, they is moving away from us, and you can measure this using measuring the redshift You use spectroscopy, and then the light that arrive here, you know, the lights when you have using spectroscopy, you can see the lines for each element that compose, for example, the atmosphere of a star. And then when she's moving away, the position of this line moves. Then you know if this object is coming in our direction or moving away. This is called redshift. And then in the Hubble proof that we have a relation between the distance of the movement of this galaxy and the redshift, the distance of this galaxy and the redshift. It's like something, this what happens. You can see here. Yeah, this is what's happening with the universe. They are expanding, and the objects moving away from each other. But what is curious about this we know, is something that we call the co-moving distance. There is this distance between two objects that, for example, we measure today. And what's happened? The universe is expanding, then this distance between the two objects is growing as the universe is expanding. And you have a factor, a scale factor associated with the expansion of the universe that will say for us in the future what will be the distance between these two objects. This we call the proper distance, that is distance of the two objects in the future, because you have a scale factor that you multiply plus the distance that we move today, the movement distance. That this will not change, will change by this factor, the scale factor. And what's curious about this, and the Hubble parameter is associated with the scale factor, and then you can measure and then define the scale factor. But what's curious is this one. What is the size of the observable universe? It's more than 90 billion light years. This is the
90.
diameter of the observable universe. We are here in the middle of this image, in the center of this image. Then the radius is almost a little more than 45 billion light years. This is the size of the observable universe, the radius. And many of these galaxies that are, or these objects that are very at this distance, that the limit of this observable universe is moving faster than the velocity of the light from us. This is prohibited by the theory of relativity, from Einstein. Then it's something that many people don't understand what's happening, because how an object is moving faster than light from us. And we know that we know the redshift, then we know the velocity of this object moving far from us. And you have an object moving faster than the velocity of the light in a vacuum. That is the maximum velocity of an object in our universe. Only light radiation can move in this velocity. You cannot reach this velocity. How does have objects moving faster than this? Then this is something very curious, because what's happening is something that you can imagine that is not only the object that's moving. It is space, the space-time that is changing also. The space-time is also changing. The space-time is growing also. Then if you can measure only the velocity of the galaxy, it's not faster than the light. But you have to also to consider that the space-time is growing. That's a different process. Then you reach this kind of velocities. Then something very curious that when you talk about the universe expanding, they imagine something that is not usual that appears when analyzing this. And this is the image that was this fantastic event. Thank you very much, Scott, for the opportunity. And soon we will have a new edition of Skies Up, and it will be a fantastic edition.
Yes.
Thank you very much for the invitation. It's a great
Thank
pleasure.
you.
Ever is a great pleasure to be here.
Thank you very
Thank you.
much, Marcello. That's great. Now, let me ask you a question. Okay, and I had the opportunity to see Alan Sandage. Okay, Alan Sandage was I guess a protege of Edwin Hubble, and Alan Sandage was still living and giving lectures.
Wow.
And I was at I think it was an Astronomical Society of the Pacific meeting, maybe in the early 90s or late 80s, something like that. And I got to ask Alan, Dr. Sandage, what would happen? Okay, he was giving us an idea of the diameter of the universe, and now we know it. We understand it to be much larger than what the numbers were before. But I said, what if I could somehow fly to the edge? Okay, if I could fly to the edge from where I am right now to whatever that edge is, okay, and then I got out my telescope and my spectrograph, and I started to make measurements. What would I see if I looked all around? If I did a sky survey, what would I see?
You see everybody moving away from you.
Right, and that's what
Because
he said.
the
That's what he
universe is
said. And
expanding.
that, I mean, mine was blown at that point.
And it's something that I didn't say that I remember now is that this is observable universe, but it's not the limits of the universe.
Ah,
Because you have
it's
parts
the
of the
observable
universe
universe. That is
that we can't see because you have a event horizon. The galaxy jobs that is after this event horizon, the light of these objects didn't reach us. Don't reach us. Then we can't see. Then what this is the difference. We have the observable universe that this now we imagine that have a diameter of with us in the center of the universe.
Yeah, we feel
the
like we're in the
diameter
center, right?
like in more than 90 billion light years. But to have probably many things after these limits that you don't know what is. We
So
don't know
maybe
the
there are
real
other
size.
galaxies and
Yeah, we don't know the real size of the universe.
Ah.
When you know, we only know our limits until where we can see. After this, we can't see. This information don't reach us. Then something that is made us, but we need to make observations because the theory it's not a closed model. We have many problems with the theory. Then maybe in the future we have another understanding of the universe, but it is the best model that we have until today.
That we have right now. Oh.
Yes.
Well, if your mind isn't blown right now, I don't know what will blow it. So, Cesar, thank you, or Marcello, thank you so much. Thank
My
you.
pleasure.
Thank
pleasure.
you.
Thank you.
Yes. All right. Okay. So, okay. So we are. We got to see the cosmologists come out in.
Check.
And Marcello doesn't like for me to say this, but Dr. Marcello Sousa, okay, he is a cosmologist and he's a good one. So we're really fortunate to have him on Global Star Party regularly. Up next is Dan Higgins from Astroworld TV. He is preparing for the second Astropalooza. And Dan, you want to come on and tell us all about it?
Sure. How's it going, everybody? Yeah, I am totally blown away. Marcello, man. Woo, man.
Yeah, you
brilliant,
start hanging
brilliant.
out with the cosmologists, and it gets way out there. So, yeah,
It got out there. Not only did it get out there, it got further away too.
it got further away. In fact, it got so far away that we can't even see it
Nope,
anymore
it's
because
gone.
it's
It's
going
gone.
faster than the speed of light. How
Yeah,
is that possible?
ran,
Okay, we
ran
don't know.
ran the Kessel Run in 10 parsecs, right?
I don't know.
So
Yeah, Chuck Allen also gives a great lecture about this, and he describes these boundaries, and you know, so
it's amazing. It's amazing.
yeah, it is amazing.
It's
That's right.
amazing. So great job to all the presenters so far. Marcello, great job. I don't know how I'm going to follow this up, but so I'm gonna make it a little light here. So like I
Okay.
normally do, if if you've seen the show, whatever, and we've seen all these wonderful pictures of the moon, of the galaxies, of gravitational lensing, which you're probably not going to get with your backyard telescope. But I mean, you sit there and you kind of wonder, and if you're new to this type of thing, this lifestyle that we call astrophotography, it's kind of tough to get into it sometimes, especially if you don't know anybody. It's a very niche kind of area of lifestyle. I call it I don't even call it hobby anymore, because your lifestyle changes. You're up at
It's a
night.
lifestyle. It absolutely is.
And if you have issues, come down to the show and watch us just talk about astrophotography. We do shows on Fridays and Mondays. Scott, I was looking at the last date that you were on. Believe it or not, it was 3 years ago.
Really?
It was 3 years ago. It was the last
Man, time has
it's
gone by quick.
tell us that
Yeah.
we went through and over COVID the last time.
Yeah, COVID created a whole time warp for a lot of
Total.
us. So
Very
I
strange.
don't want to go through another pandemic ever.
No, I'm done.
Yeah,
Once a lifetime, I'm good.
Once in a lifetime, that's good enough.
I'm
That's
good.
right. We don't need twice. So
Who knows what the next epidemic could launch?
Oh no,
What
don't
new platform? Holograms.
Yeah, you know what? It's going to be virtual reality, imaging. You're going to be imaging in your bedroom. It's
that's
going to be
right.
just
In your shower.
I would love to see myself doing that right out the bedroom window.
Yeah, there you go. Just look, and it gets imported in all around you. You're living in the universe.
Right.
But tomorrow, I mean, I just got a really good news tomorrow night, and I'm gonna show something really quick here. Now this was taken at NEAF last year, and this gentleman is Jeff. His name is Jeff, and he's from Dark Dragons Astronomy, and he's going to be on the show tomorrow. And I know you can't hear it. I'm just playing it. So
Sure.
it's an observatory. It's a roll-off roof model that it was really ingenious, and it's super light. This is the floor model, so if it looks kind of like shoddy with the wood and everything, this they actually put together at NEAF, and so
That's cool.
yeah, so it's your basic roll-off roof, but it's fully safe and fully run, fully ASCOM, everything. And he's going to be on the show tomorrow night. So if you want to come and hang out with us tomorrow night, you're more than welcome to do that at Astroworld TV on YouTube. So it's going to be a lot of fun. I met him at NEAF. He's a great guy. If you follow him on TikTok, I think it's Dark Dragons Astro. He's a super funny guy too. So it's a lot of fun. But
I'm going to put that link right here in the chat. So you guys want to bookmark that. And what time will you guys be on tomorrow?
Tomorrow's Wednesday, so it's 9 p.m. Eastern.
Okay.
And then Friday we do the beginners night, and we kind of talk about, we do me and Eric do one constellation each usually, and try and find some things in constellation to image. Sometimes it's really hard. Try and find something in Equus. It's kind of rough to find in some random parts of the sky. Actually, some things I can take a picture of. But on December 9th, you can see up in the top left-hand corner, we have Astropalooza 2 coming up. And I know, Scott, you're going to be there.
Right.
And it's December 9th.
December 9th. I was like confused.
December 9th.
Okay. All right.
So Let me see if I can get the lineup here for us. Let me see if I could do this. And I'll get me, oh, wow, I got a lot of overlays here. Let me see if I can get rid of this real quick. Layers. Let's get rid of me. Go away. There we go. All right. So here's the lineup, and it just disappeared on me. And
There it is.
boom, boom. There we go. So there it is. So we got a huge lineup this year, and this is starting at 2 p.m. Eastern. It is literally going to be like 8 hours of some of the best in the business, including who was just on the show before the break, Ron Breacher and the Masters of Pix Insight is going to be on as well. And we're also giving away free Masters of Pix Insight workshops all day.
Wow.
So that's going to be cool. We also got a signed book from Charles Bracken, The Visible Universe, along with, if you saw it at NEAF and NEAC, he had a picture of his all sky photo, which encompasses, and I might mess this up, of 2-hour panels, 139 different panels.
Oh my God.
And it's an all sky taken with, I think, 3 telescopes across the entire planet. And it's all overlaid. And if you haven't seen it, go check it out. It's on the Visible Universe website. I believe it's
Visible Universe. Okay.
Yeah, Visible Universe. And that's the name of the book. But it's really amazing. It's a nice book. But we got Trevor Jones, we got Dylan O'Donnell, Sean Nielsen, Astrostace, obviously Scott, Masters of Pix Insight, Charles Bracken, Dr. Sass. We got Prima Luce Lab coming down to show us some of their new stuff. And the infamous Wayne Parker from Skyshed Observatories is going to be on as well. So it's going to be a huge event. They're all doing about 30-minute to 45-minute presentations. And it's going to be a lot of fun. Again, we did it last year. It was a long show. It was 9 hours, but
it's long.
It's long. It's long. It's. And I think I said it last week. I did end the show with a shot of whiskey. I might have to end it with 2 this year, but
just leave the bottle there.
If I did that, we'd be in trouble after about 3 hours. So
they do have that show. I think it's on YouTube where they have movie stars or whatever, and they get them drunk, and and then they have to answer like questions about history or something. So.
And I saw something. What we always talk about on the show, on our show and your show as well, about our expanding of knowledge of the universe and the things around us, and all that type of stuff. So I'm watching. Of course, I got to bring hockey into this. So I'm watching the Islanders game the other night, and they took people from all over the league, players making millions of dollars, whatever, big time players, and they said it's like name 3. So name 3, and so there's a topic, and you got to name 3 things in that topic. First thing was like 3 movies. Second thing was like 3 Harry Potter characters. Third thing was 3 planets.
Uh-oh.
Can I tell you, there was 20 people that did this.
Yeah.
1/4 of them said the moon was a planet.
Well,
it is a world. It was planted by the aliens.
It is a world.
But that's like saying Pluto's a planet. I mean, go on.
I'll take Pluto as a planet.
That's a discussion for another time. I did a whole write up on that in college, and I was like, we'll just that's a very touchy subject with me.
Can I say something, gentlemen?
Absolutely, John. Go right ahead.
No, I was going to say you might want to get Seth Shostak because the moon could have been planted here. You never know.
It could have been. So, just like, Superman went around backwards around the planet a couple times, and made it go back in time. You never know. Maybe it was dragged in from outside the solar system and just parked here. Definitely could have been.
It was accretion.
Yeah.
But it's funny.
Yeah. I mean, I thought it was funny. And then there was some people that said, that only named one. But anyway, but
They only named one planet.
and it wasn't even the Earth. But so
yeah, people forget they're standing on one, right? So.
I remember it was somebody when I was working in a telescope store in a shop. Somebody said, it says I could only see 8 planets with a telescope. That was when.
Oh my God! Okay.
And I was like, why can't I see 9? I said, point it down. So he's like, oh, but anyway, I know it's late. I know it's an hour late, and I know we want to move on and get the show going on. But thank you, Scott. So come on and hang out with us to Astropalooza. See us tomorrow night on with Dark Dragons Astro, and just come on and hang out. On Friday night for beginners night. It's a lot of fun. So
awesome.
But thank you, Scott. Have a good night.
Thanks for gracing us here with your presence here, and we look forward to more Astroworld TV and the Astropalooza.
Thanks for having me, Scott. Appreciate it.
Take care. Bye-bye.
All right. Bye-bye.
Take care.
Later.
Okay, so up next is our night sky photographer, our landscape photographer, our artist photographer as well. Adrian Bradley.
Yep, it's me. Can you guys hear me okay?
We hear you just fine.
Good.
You're out there in the Milky Way, dude.
Yeah, that's pretty much where my head is at. My opening commentary, because we're talking about the size of the universe. Of course, where we are, sometimes folks' universes are only as big as their experiences. And what I try to do, rather than talk about the entire size of the universe and in all of the theories we've heard about, do we really know how large it is?
Or how
I use my photography to just try and point at things that you can see with your naked eye, realize how far away they are, and try and say the universe is bigger than all of us, and see if that try and give some perspective. Whenever I do outreach, I typically get sort of don't believe I'm seeing this. It's
sure.
How far away is it? It blows people's minds for the couple of hours that we're doing the outreach. Tomorrow brings along its own problems, and it sticks with some of us. It's something that we want to learn more about. Sure. I do hear a lot of, I want to learn how to use this telescope, or lately it's, I want to learn how to do astrophotography. But to do astrophotography, one of the things, either it's going to take a lot of time, money, both. You do have to be committed to doing that sort of thing. And there are a lot of things in the universe that are, because of its size, there's so much that's out there that you can image. I will go ahead and share my screen. I will share just the screen because I think that'll work. And there's my email that I'll put away, and then I'll bring it back because I want to go.
Orion, I saw that. Nice.
Yeah.
Barnard's too.
It's nowhere near, it's not quite near the brilliance that when Maxi comes on, you see this total solar eclipse. But this view is the most breathtaking view I've seen of our universe, and captured it using a modified camera so I could get all the HA.
Now that's
all of this nebulosity that's around Orion shows up. This part of the Milky Way shows up, which you hardly ever see when you're in my climate. You hardly ever see it. There's more to it that I haven't even. This is the Rosette, which is a very popular target, but I actually do like this image to talk about size of the universe. You'll see this Rosette blown up. Beautiful images of it by a lot of deep space astrophotographers. But if you compare it to everything else from our point of view, it's it's not very big. It's this sort of a pinkish dot with, white in the center. A lot of these, the horse head that everyone loves is so small it's here. And then you can see the Orion Nebula over here. There's the companion NGC 1977. This big loop, which I believe folks are saying it may be a supernova remnant, Barnard's loop, is a large structure compared to these others. This nebulosity here, Lambda Orionis, this giant. And look at, the size of the star Betelgeuse, compare it to the size of the Orion Nebula. Now, there's a lot more because of distance. There's, sizes may vary. This is compared, to where we're looking, but the larger, 1.3 light years across, as opposed to, it's very much a giant and would swallow up our solar system. But even though the two look kind of similar in size from our vantage point, that's a whole lot larger. And it starts to make you think, this is a pretty big hill. If I jump from here, I'm probably jumping to my doom. But the size does not compare to the size of this star right here, which this is the star Sirius, which I think is, I want to say it's 8 light years away and is a blue giant. The scale of the universe sometimes blows us away. All of these stars that are here, all of them could have, won't say all of them, it depends on where they are, and but all of these stars could have worlds going around them. When we process images, and I don't know if I'm moving this if this gives more of the image, makes it visible, but when we process, if we're just going for pretty pictures, we might take a lot of stars out. We say, well, we're focusing on certain things. This is the zodiacal light, by the way, for those who have not seen it naked eye. It is, along the plane of our galaxy, the spring solstice and the fall. I think it's the spring and the fall equinox. I said solstice, but that's for winter and summer. Spring and fall equinox, the plane of the galaxy and the dust that is along the plane of the galaxy can be seen at an angle. Orion actually sits near the ecliptic. This is basically the ecliptic. You've got M44 here, which is in Cancer, which is one of our, of course, one of our zodiac signs, and Leo is back here. These are the stars of Leo. Do believe this is Regulus right here. Leo's following, there's Cancer, and there's the stars of Gemini. So this zodiacal light always goes along the plane of the ecliptic, our plane of the galaxy. Planets will end up here. And the moon always ends up, when you see the moon, you tend to see it along this line. And but the distance between what we can see in our solar system compared to how far away this is, it can blow your mind. And we're getting all of this from just looking at one image. And finally, dwarf galaxies, we would have to go just about equidistant to how high Orion is above this horizon, down below screen, about that same distance, maybe a little more, and you would see the Magellanic clouds of the southern hemisphere. This picture is taken from Oklahoma. The further south you go, the more of the lower part of the southern parts of the Milky Way galaxy you see. And and it goes out as far as you can imagine, unless you read publications where science is done to try and figure out just how large we figure out how large our observable universe is, and then realize we have a certain limit to what we can see. And to me, all of it is just humbling. So really quick, I will close that because I didn't want to.
I wonder how far the center of our galaxy is Sagittarius.
30,000 light years.
30,000.
30,000 light years, and yet you can see it like this. And you can see it like this. 30,000 years. And all of this, this image, I'll say it's a little overdone, but it's reminiscent of the type of images where you process it in order to make the Milky Way your star. And when you process like this, you do see a lot of nebulosity that really is there. And this is a pretty decent dark enough sky. These are really, you can see these naked eye, and even M11 shows up. I do believe right about here is M11, M17, M16. A lot of sharp objects here. Yes.
Your work, it just, for me, it's like, I mean, astrophotography is awesome in its own way. But when you take your pictures, it really brings me to that place. Like I'm actually out there with you and we're seeing this just going, man, is this how far? It's like, right?
Yeah, that's my goal with all of my images.
Yeah.
To show what's there and make it the star. And for those of us that are in northern climes, you're seeing an image of the Milky Way here, with my modified camera that shows a lot of regions. This region was used for a study to try and find exoplanets. Body's window is somewhere near there. A couple of globular clusters. I don't think they quite show up here, but that's the window through which all of this dust and gas you're seeing, it's a window through which we can actually see closer to the center. The galactic center, of course, in and around where this star is sort of a pointer to the area where the galactic center is. But from our vantage point in Earth, can't see it. Now, if you're at a good night and a good dark site, you'll see this nebula, or this, nebula, this cluster, which is the butterfly. I don't know if I can zoom in. It doesn't look like. That little thing is M6. This is M7, Ptolemy's cluster. Over here, you're seeing the lobster claw, the cat's paw, and the prawn nebula. The rest of the scorpion, and there's a cluster down here. I think this may be it. The rest of the scorpion comes down and sweeps down to the horizon. There's only a few times you can see that. And for all the astrophotographers up north,
could start to give planetarium shows at this
definitely point, Sagittarius is over here. Yeah. And there's, I believe, M22. I think I missed M22 in this particular shot, or this has been cropped in. The full shot shows all of Sagittarius and all of Scorpio, and it was a hazy night too, and we still got all this detail from a 16 millimeter lens and a Canon 6D that's 14 years old. Astrophotography isn't so much about your gear, it's about how steady your tracking is, how much light you can pull in, and the processing tools you use to bring out. We call all this data until we bring it out. And if you get good data, you see a lot of things when you process, whether you're doing a 35, this is a 35 millimeter image tracked for 2 minutes. And there's just a lot of data here. M4 is over there. We just lost it. Now, comparatively, and not as dark skies, you see some of the same things. You just don't see as much. And this sure looks like it's turned over on its side for whatever reason. I did this meteors or satellites. If you're there and you see them streak across the sky as you're taking the image, then you know what they are. If you don't see them, then chances are you're looking at satellites. Like
beautiful galactic clouds there, Adrian.
Yep. Look at this
Wow.
rift. Any
That
good
is-
image of the, this part of the Milky Way
Yeah.
is now gone in the northern hemisphere. Southern hemisphere, I believe it still may be visible to our friends in the southern hemisphere. At least the other side of this is visible. And this is where I'm going to stop the presentation because I know we are running late. And John, I'm giving you all the time to close us down.
That means I got more time. Thank you,
You got
Adrian.
more time.
No, I don't.
And so,
I
yeah, it when in we to what I know I said it last, sort of spread the gospel is the subject. Without it, what would we be taking images of? And I can answer that for you. You would have to do images like this, where you're capturing a parade and capturing smiles on people. Nothing wrong with doing that at all. I'm not showing it because I stopped sharing. Real quick, let me do this screen.
You look great tonight, Adrian. You're color coordinated, perfectly blended.
Yeah. So, what does all of these elves and Santa and the universe have in common? Well, and this bowling ball that I like. What does it all have in common? Well, we're all made of the same stuff.
That's right.
I always encourage folks to think about what it is that you're imaging. Think less about gear and how you do it. And yes, you can be enthusiastic about doing astrophotography itself. That journey alone is a fun journey. But think about the actual universe that you're taking a picture of. The more we respect that, the more our images show our respect for that which we're looking at. And we're not just using it to make a quick buck or post online. And a lot of the top astro imagers, they share their images, they do outreach, they are selling those, they're selling those images, and they aren't too fond of seeing images from folks that they may not know that rival theirs, and it looks like there was less work taken to do it. It'll rub these longtime astro imagers the wrong way, but the universe belongs to all of humanity. So we just we come together as a group of amateur astronomers, visual observers, folks like you, John, who you do a great job of drawing out the universe, which is coming up.
I got
all
a
of
lot
us
of
are aiming at the same thing, an unfathomably large area in space-time, that we're made of the same stuff and we belong to it. And with that, Scott, I will turn it over to you.
Okay. All right. Thank you so much. Thank you so much. We're going to bring on
Nice seeing you, Adrian.
John Schwartz. And you have a good night, Adrian. Thanks again.
Adrian,
Wow.
Nice to see you again.
Good seeing you, John. I am looking,
Man,
my monitor is upward, so every time I'm looking up like this, it's so I can see the screen. So that's where that's coming from. I look at the camera. I have to point, I guess that's going to be my new thing. I'm going to point at the camera every night. But this time I was able to bowl well enough, John, so that I could get home and do this presentation on my main computer. Last couple of nights I've had to do it on my phone, but it doesn't stop the show from going on. So
I was curious
about seeing
you. That's right. On the road, at the Texas Star Party.
I was at Okie Tex, and I jumped in. I remember, or I was in Denver, I think, and I jumped on.
It must have rained there.
It was cloudy the whole time there. I won't take over the screen, but I have pictures that I took of the skies we had both before, after. It was cloudy. I had storm pictures. And I think I've shared those on Global Star Party. If not, I'll be sure to share them next week.
Maurice had one of those cloud filters, my friend.
Maurice, I don't know. Adrian, do you even know who Maurice is?
A comet filter, something like that.
Yeah. Well, most of the time I have a lot of cloud filter. This is Michigan, so we get one clear sky night per every 2 weeks.
We used to just wait, stay up and it's all cloudy. There's going to be a sucker hole coming soon. So we get the hole and everybody's like trying to see something. You have to have slewing to follow it, through the hole. But
yeah,
sometimes
we did that at Okie-Tex. We chased sucker holes. They closed up on us. We made the most of it.
Well, the camaraderie, seeing everybody and being a part of that event has got to be amazing. I'd love to go one day.
Yeah, it was.
Okay.
All right.
Well, you've got the stage here, John.
Well, good to see you all. So it is an old universe, I feel old. I mean, I'm so old. I was around when the Dead Sea was only sick. It's a long time ago. The universe is I'm not quite sure. It's got to be, how many years would you say, Scott? Billions of years? Or
the universe? The age of the universe?
Age would be about 14 billion, and we're still working on validating.
That's just as far back as you can see.
What's that?
Is that what James Webb can see? That's how far they calculate we've gone back, like a couple billion years
There's this
after.
thing called the observable universe, okay?
Right.
And then there's the universe. And it looks like none the tween shall meet here, because the further out we go, the faster things are receding from us. And as Marcello was describing, there's a point where things are going faster than the speed of light and we can't see it anymore. So, if we can't see it, does it exist? It gets
almost
into philosophical questions, about what is reality, and so I often tell people when we're talking about light years and looking back into time, because amateur astronomers will often refer to their telescopes as time machines, because they're looking out millions of light years, or in some cases you can see things that are a few billion light years away. And but the truth is that even someone standing right in front of you, it takes some time for the light to get to you. It takes some time for your brain to process an image through what is the image that's falling on your retina. So you're always looking back into time. And if the past does not really exist anymore, then what is it that you are, that you're calling reality? So it gets a little spooky out there, and makes some people feel uneasy, so but amateur astronomers are always dealing with these kinds of things, and of course the cosmologists try to get better and better models of what this is all about. So
the past is just a collection of all the photons you've seen throughout your life, and the memories are, you just look back and be happy about all the good times, and the family, and then the stars. I mean, it's just amazing.
It's amazing stuff. That's right.
But you don't want to look back and use that and bring it up if it's not a good thing, because that was pretty much yesterday. We live for today. That's what we hope for every day, another day.
Right.
But anyway, so It's old. I mean, just to get to the nearest star, right? It would take us 4,000 years at the speed of light. That's incredibly far. Imagine the generations of how long it would take to get there. You'd have to have children on that ship and travel quite fast to get that, I think, speed of light. It would take a while to get going that quick. We always look out and think of how far things are, but then when you translate it into how many million light years away it is, it took that long for light to get here, and you're seeing it back then. It's mind blowing. I mean, just kind of sets you back and gives you a little perspective on how small we are and fragile, yet we're conscious.
That's good. It's good to have that kind of.
It's just amazing.
Yes.
So the Hubble Space Telescope, or that's Hubble, I believe. Beautiful image. The what's that band? The Hubble Palette, and
yes.
Before James Webb, that was the benchmark. I converted it into black and white, and then we were trying to see what we could get, and that's our image. Wait, no, that's still Hubble. That's my image through the 28. And if you want to get it done quick and fast, if you can get enough frames, maybe 2 to 5 second frames, stack them, you can get some amazing results. So this is taken from Earth right here in Southern California at Mount Pinos. Mirko took it for me through my telescope. Quite amazing, brings you real close, a lot closer. That's what we're trying to do, is see the best view. I think everything's great, drawing, viewing is the purest. You never want to stop viewing. Astrophotography, my God, what you see some of these people do is absolutely amazing. Gorgeous. It's art. It's art too. The processing, the technique, it's a lot of work. It's a very meticulous trade, and you have to be diligent to do it. And you do it because you want to share it and take people there and give them the best view. Not like those department store telescope boxes we used to get. When do I see that? That's actually Mirko's 32-inch. I think it was a couple second exposure. The Eagle. It's one of my favorites. This is my latest. So this is actually how I see it in the eyepiece when I look. 5,700 light years away. So that light left there that long ago. And supposedly, I think one of the telescopes, maybe Chandra was it, or one of them is offline now. It does X-ray, I think. And they said there's perhaps a supernova that went off in there. And that thing may be not even there anymore, the Eagle. It could be blown to dust because of that exploding supernova, and we just haven't gotten the light yet. It's a speculation, but I've heard about it. You like that one, Scott?
Love it. I love the it looks mysterious,
Yeah, that's the
and that's often the kind of feeling you get when you're visually looking through a telescope.
It's so hard to capture that essence. This has taken me. I mean, it just never looks right until you stumble onto it. And the next morning you wake up and you turn on your phone and look, and you're like, yes, finally.
Mm-hmm.
There's another version, just hazed out, with it's just the light on the dust, cool. Different effect.
Yeah.
But man, 5,700 light years to get this close, right? That's what I see on my best view through the 28 and the 32 on the clearest, darkest nights. We haven't really experienced this at Bortle 0 or Bortle 1. That could be absolutely amazing to see what you can see naked eye.
Mm-hmm.
The sun is what, 8 minutes it takes for the light,
right,
to get here. That's pretty crazy. This was my eclipse sketch the other day. I combined the initials, when I was burning my eye, squinting at it, which wasn't smart. Don't do it. Always protect your eyes. And then I wanted to give you all some leftovers from Thanksgiving. It's a lunar omelet with cheese. What do you think? It's plated.
Yeah, I'm hungry. That's
The
what I'm
dish.
thinking.
I've posted this on Cloudy Nights. I don't know if I thought it was fun and creative. It's a different look.
Sure.
And, as an astrophotographer, you want to be creative and you want to change the look. If you use those, what are those filters? I'm like drawing a major blank here. Not the Hubble palette. They're sodium, oxygen, and not tricolor. There's the name.
Beta? Is that what it is?
No, there's
You're talking about the
different
3 filters that they use for the Hubble palette?
narrow band. It came to me.
Yeah, they're narrow band filters. Yes.
Right. The moon, this was just, so, you don't need much. You could just get a pair of binoculars to see something like this. I know it looks very simple, but it's actually pretty complex. The color theory, to get it to, you have warm and cool light play, and then, you also have the earth shine and the nice shape of that, just the right angle shape, very contemporary. That was my neighbor's house. I got lucky. That's the thing. When you're out, sometimes you get lucky. You get that view and you capture it. And then you're like, wow, this is amazing. That was my blinker,
Yeah.
Star blows up. It takes a long time. That supernova they discovered a few years back, they have pictures of it that Hubble's been taking. But VDB 108 or something, I forget. It's a red one. You've seen it where it expands. And this is the blinker. The thing is, in my telescope, it never blinks.
It never blinks. You got enough light.
But look at that. Does that have a dimensional feel to it? Like it's encased in, that's the essence I'm trying to capture. That's very difficult to get it right. But I'm not sure it's quite right. I hope it looks good on your screen. Looks good on mine.
Looks good.
Cool. They never look as good for some reason. You need a 4K monitor. M33, what is this? 3.2 million, part of the local group. I like to do versions different. This was one of my earlier versions.
I like these.
I was eating popcorn and the salt fell on there, and I saw that and I liked it, so I just stippled it a little bit. Actually, I'm kidding. I just painted that on there. It took a while to do the stars. They're not probably correct, but. And this is the evolution. Now, this is adding Malincam data. So what I do is in the side-by-side mode, I take a look at my Malincam image, and then I have my other image right there. It's on Procreate. It's the split view. And then I can draw, and it's very close to where your eyes have to travel in order to, sometimes I'll be drawing and I'll forget what I just looked at. So I have to keep going back and forth to keep it in your mind imprinted so you can, duplicate it on the other side. So, these are great because the evolution of these, it keeps going and going.
Yeah.
The more bigger scopes I look like, and I go to the 60 or the 100, if we do the 100, boy, I might be getting closer to getting out there. That's what I try to do with my work, is I really want to bring you there as if you were actually took a trip out there. It's just a visualization sort of.
That's spectacular.
M74. This is another one that's far. Now you want to talk about getting further. This is 30.6, I think, million light years. And that's getting out there, not quite. There's some that go way out that we look at. Like this one, 3338. I think this is maybe 80 million or something like that. I could look it up real quick. I just can't remember off the top of my head, but it's getting way out there. Now we're gonna move on to a couple more works. This is my Jennifer Beals painting that I did. I like to show a little artwork here and there. And this was actually a watercolor picture that I did in college. Very proud of. It's the only piece that didn't get burned in the fire. It's kind of a special piece to me.
Yeah.
But you know, look at the painting. It's gouache. That's also acrylic. Not acrylic. There's a little acrylic gouache here. That's airbrush or color. I was a lot younger then, so my eyes were better. But digital has been amazing for me. Really has. Now, always having your camera ready. You never know what you're going to see. A beautiful flower on a crystal blue day, reaching for the sun. You know, the life force.
Yeah.
It's amazing how plants follow the sun, and flowers when they open up in the morning.
Years ago, I went to a star party, and there was a lady that gave she was an astrophotographer, but she gave a presentation. It was just like galaxies and flowers, just bouncing back and forth, you know, and it was
Wow, that's
actually
really cool.
It was a wonderful presentation.
I mean, if you look at the flower, it's almost like a spiral galaxy, the way it, you know, the physics, and think of like the microscopic universe. You know, you're talking how actually far or how old something, but it's very similar in construction. The physics behind it, it's kind of cool. This was the neighbor's house, and you know what's crazy is these flowers are gone. I have pictures of these flowers when they were, you know, alive and just reaching for the sun. And when they tenant left, they just put that turf in there, that astroturf or whatever. So those are gone. And the other neighbor cut this beautiful tree. I'm going to show it on the next one. Maybe it was such a cool tree. It's gone. Poor tree. Boss, you know, my little buddy, he's always got to say hello. He's truly a good friend. And also, I think he's made of stardust from the constellation of puppies. I believe. I'm not sure.
Oh, yeah.
The dog star. Serious.
Maybe
I'm not kidding. No. You know, the star. There he is. He gets frisky on me if I ignore him. You know, if I'm doing stuff, especially astronomy, he'll sit there and just wait, like when I'm doing the moon pictures I do.
Yeah.
And I have to like keep him close because I don't want anything to get him in the dark. That was in the morning after a 2-day star party. We came home. He was shot. I was wrecked. You know, when you do this hobby, it's a lot of work, but it's well worth it. I mean, everything we do, it just helps us understand, you know, how we fit in and why we should do it. And that's my presentation. I want to share one last picture that Mirko took. Again, this is amazing. This was 18 2-second exposures. Is that amazing?
Very nice. 18. You said 2-second exposures?
Sorry. My granddaughter was coming in. I want to have her come on in a few after we get the rehearsal done. We're gonna sing Twinkle, Twinkle, Little Star. She's going to teach me. I hope I can learn it because,
Yeah, it's a tough song. It is.
I was thinking of changing the harmony, create a little different take on it, but we'll keep it legit.
Okay.
Anyway, thank you so much.
Thank you so much, John. Thank you for your program. And we will be back with making announcements for the next Global Star Party. We have um, we have some plans. I'm working it out with Dr. David Levy, and it will be, I think, very interesting. So, but it's been a blast to find those full-length lectures from Bart Bach. And if anybody out there wants them for, like their astronomy club or something like that, let me know. I can get you we can transfer the original files so that you can use them during your presentations. So, really, wonderful educator and very inspiring astronomer. And I think that I'm lucky. We're lucky to know people that knew Bart Bach when he was living. So, but we hope that you have a good night. I was out just a little bit during the break looking up at the moon, and it's a real clear night here in Northwest Arkansas. So until we come back with the next Global Star Party, keep looking up and, contemplate the universe.
Thanks, Scott.
Take care. Good night.
Have a good evening. Thank you, everyone.
Come one, come all to the Southern Cross Astronomical Society's 2024 Winter Star Party, celebrating 40 years of stargazing, happening from February 5 through the 11th, 2024 on Scout Key in the beautiful Florida Keys. Get away from the cold and adjust your latitude underneath the pristine skies of southern Florida with breathtaking views of Eta Carina, the Jewel Box, the Southern Cross, Centaurus A, and of course, the magnificent Omega Centauri. Tickets will go on sale on or about October 1, 2023 at scaz.org. See you there!
Are your eclipse glasses safe for looking at the sun? Let's check to see if your eclipse glasses can handle the heat or if they need to stay inside. First off, never check your eclipse glasses with the sun. That's a good way to injure your eyes. Take your eclipse glasses and find a bright light, like a lamp or a flashlight. Hold your eclipse glasses up to the light and look through them. The light will appear extremely dim or not appear at all when looking through the glasses. For example, you should only be able to see the filament of a light bulb, but not the glow surrounding the bulb. Also, if your eclipse glasses have any marks or scratches on them, don't use them. If you have older eclipse glasses from a previous eclipse, give them the check to make sure they haven't been damaged or scratched. All safe eclipse glasses will meet the ISO 12312-2 standard. It's best to store eclipse glasses in a safe place where they won't become scratched or punctured. Remember, never look at the sun without eclipse glasses or a solar filter. Be safe and happy sun viewing, everyone.
Targus is on a mission to create smart, sustainable accessories to empower you to do more by using less. It shouldn't be a barrier to tech. It should be seamlessly integrated with how we work, play, and live. That's why we're on a journey to create a suite of tech accessories where smart design and sustainability are inextricably linked. We're doing more, designing smarter, dreaming bigger, and using less. Introducing the EcoSmart range of bags and accessories, a collection of products that not only puts the planet and people first by using a host of eco-friendly innovations and materials, but enables you to do more with your device while protecting and empowering your future. It's our planet, your future. Together with Targus, you've got this.